मंच एक खुला मंच है, आए जब भी चाहे। किशोर मंच एक खुला मंच है, आए जब भी चाहे। हर किशोर को मिलेगा अवसर, खुलती जाए राहें। आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे, आए जब भी चाहे। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान। हो कला सामाजिक ज्ञान, भाषा गणित या हो विज्ञान, कठिन नहीं है विषय कोई भी, करो जरा सा ध्यान।
ये है
किशोर मंच।
In this lecture, we start with magnetism. The magnetic field of the earth is something like this. The earth behaves as if a very strong magnet, bar magnet, is placed inside it. Of course, there is no bar magnet, but the lines of force or the magnetic field lines that we draw, they indicate that the field is dipolar. The magnetic field at any point on the earth is defined by three elements. What are these elements? This declination d, horizontal component h, and the angle of dip or inclination. I will show you in a moment. Remember that the magnetic field of the earth has no regular pattern, and all these elements vary with time. They are not fixed, they are not constant, they keep on varying with time. And if you want to find out the magnetic elements at your place, please visit this website www.ngdc.noaa.gov, and you can feed the coordinates of your place and you would get all the elements. I will show you that how I have got the elements at Delhi. The line joining the magnetic north and magnetic south of the earth is called the magnetic meridian. This red line is called the magnetic meridian. But what is a meridian? We have to learn this from spherical trigonometry. You see, any circle on a sphere which passes through the center of the sphere, any plane circle passing through the center of the sphere is called a great circle. For example, equator is a great circle because the plane of the equator passes through the center of the earth. Horizon is another great circle because the plane of the horizon passes through the center of the earth. Then a line joining or a circle joining, half circle joining n with s is called a meridian. It is a half of a great circle. The full will be a great circle. The meridian is only half of a great circle. And this meridian you are familiar, because this gives you the longitude of your place and therefore, the time of your place with respect to the universal time. So, the meridian through the north and south poles of the earth is called the geographic meridian. This is the geographic meridian, and if we have north magnetic pole and south magnetic pole, then the meridian through that would be the magnetic meridian. And the angle, say here I show you the magnetic meridian, and this is the geographic meridian at a given place. The angle between the geographic meridian and the magnetic meridian is called the declination. That is, if this is the geographic meridian and this is the, I have shown you earlier that there is an angle between the magnetic axis and the Earth's rotation axis, this angle is declination. The angle between the two planes, magnetic meridian and geographic meridian, is called the declination. In the magnetic meridian, the horizontal component of the magnetic field is denoted by H, the vertical component is denoted by V, and the total field is F, that is V square plus H square under root. And the angle between H and F is called the angle of dip or inclination. So, the three elements at a given place are D, H and I. The declination, the angle between the magnetic meridian and the geographic meridian, 1, the horizontal component of the Earth's field, and the angle between the horizontal component and the total magnetic field. That angle is the dip, angle of dip. That means, the total field is in this direction, and we can resolve this into two components, horizontal component and vertical component, through this angle I, the inclination. Same relationship I show here with a little more details of geography. And what is the angle of dip? If I have a needle, magnetic needle, which is free to move in a vertical plane, then at a given place it will settle at a certain inclination. This magnetic needle has settled at an inclination I. I is the angle of dip at that place, angle of dip or angle of inclination. The other two elements are D and H. The horizontal component of the Earth's field is denoted by H and the vertical component by V. The angle between H and F is called the dip or inclination. The figure shows you the magnetic field intensity around the Earth in 2005. You can go to this site and see this map, and what you see is that there is no set pattern or any discernible pattern that this horizontal component has, and this is because of the fact that magnetic field keeps varying all the time. The strength of the Earth's magnetic field is around 0.5 into 10 to the power 4 minus 4 Tesla, or 0.5 Gauss. Gauss is another unit of magnetic field. To give you an idea of the various elements of the field, their approximate values at Delhi are given here. You see, I have found these values from this site. So, you can do for your own place. At Delhi, the declination is 1 degree, horizontal component is 0.34 Gauss, vertical component is also equal because declination is almost 0, and the F is 0.5, inclination or dip is 45 degrees. That is why H and V are equal. All these values are changing with time, though not regularly. You see, they change, but not regularly. For example, declination changes at a rate of 1.4 minutes per year. So, this shows that the Earth's field is variable, and you can see from this figure, this magenta line shows you how the north pole of the Earth has drifted in the last so many years. You can see this magenta line, you see it started from here. So, you can see the magnetic field varies and its north pole wanders around. At present, its location is roughly this. Again, all these details are given on this website. The important thing is, or interesting rather, not important, interesting thing is that for so many last so many years, people have done experiments, they measured the magnetic field of the Earth, and it is decreasing. That is what gives rise to the fear that it may be flipping. You see, in the past, the Earth's magnetic field has flipped many times. I will show you this. The minerals which contain iron at a particular time in the history of the earth, they fixed the magnetic field at that time. So, by studying the volcanic rocks in the earth, we can find out the direction of the magnetic field, and that is what I am trying to show you here. In the Atlantic Ocean, there is a ridge in the middle of the ocean. This is called the ridge, central ridge. And what is this ridge? What does this tell us? At this place, the magma from the earth, from the place just below the earth's surface is coming up. Magma, is the thing that comes out of volcanoes, and then when it comes out, it cools and then it becomes rock, and the minerals in this rock can record the direction of the magnetic field. So, if you study the rocks around this ridge, you can find what the direction of the magnetic field has been in the past. So, this is the ridge, on the edge is on this side and on this side. This is the present moment, and you can see these stripes. These stripes are this is the normal polarity, so called, and the light blue ones show the reverse polarity. So, you can see it has reversed from normal to reverse, normal to reverse, and so on. So, in the past there have been several such reversals of the earth's magnetic field. Here the magma is coming up, and this, when it cools, then it solidifies the magnetic field at that time. The age bands preserved in the oceanic crust can be matched with the patterns of magnetic striping. The earth possesses a magnetic field which acts rather like a bar magnet with the earth. This magnetic field possesses north and south magnetic poles, all that I have told you, which are located approximately at the geographic poles of rotation. When magma is injected along the mid ocean ridge and cools, the iron bearing minerals within the magma align themselves according to the earth's magnetic field. So, they preserve a record of the orientation of the earth's magnetic field at the time of crystallization, and this is shown here, and we see that there have been several reversals in the past. The field is decreasing. It has been observed by the British Geological Survey that the field is decreasing since about 1840, and therefore, now people are asking questions. There are in fact popular articles in newspapers, magazines, whether the earth is going through one of its reversals. If we look at the trend in the strength of the magnetic field over this time, we can see a downward trend. We also know from studies of the magnetization of minerals in ancient clay pots that the earth's magnetic field was approximately twice as strong in Roman times, that is about 2000 years back. Observations like this have prompted people to inquire if a reversal of Earth's magnetic field is imminent. Of course, nothing can be said about the time of actual reversal. What we do now is that magnetic north pole was at the geographic south pole a million years ago. It was at the south pole. This map shows how, starting about 789,000 years ago, the north pole wandered around the Antarctic, and then it goes and settles in the north, with the north magnetic pole in the Arctic. Image courtesy University of California, Berkeley. I have taken the image from there. You can also go to this website and see this map in greater detail. What is happening? The Earth's north pole was at this point in the Antarctic and geographic south, and this wandered around this for some time, and within a short time it flipped from the south to north, geographic south to geographic north. And since questions are asked about the earth undergoing a reversal of magnetic field, there are also worries whether it would affect us. There are generally questions about the dangers of magnetic reversal. So, to the best of our knowledge at the moment, we can say the following. no geological or biological records have been found indicating large scale catastrophes on the earth. In the past, there have been no catastrophes associated with the reversals, neither geological catastrophes nor biological catastrophes. However, our modern power grid system could be damaged by the currents produced by decreasing magnetic fields. Remember that if the flux of the magnetic field decreases, then EMF is generated. So, if this magnetic field is decreasing, there is a change of flux, and therefore, there can be currents, and these currents can damage our power grids. This power grid system can be damaged. This was not existing say 1000 years back. So, we could not know, but now since these magnetic these grid systems, power grid systems are there in every country, they can be damaged by the currents which are produced by the decreasing magnetic field. More importantly, I told you that magnetic field acts like a shield. It prevents high energy particles from coming to the earth and affecting us. That is, we say that magnetic field acts as a shield. This shield could weaken because the magnetic field is decreasing. This shield could weaken, and this could allow high energy particles to reach the earth, to reach the surface of the earth and affect us. It's felt that if this happens, there will be a higher incidence of cancer on the earth, but this is just an idea. Nobody has calculated anything. Long term instability of the field before actual flip could pose greater danger to life and living. What do I mean by this? I showed you that the pole wandered here for a long time. That means, during this time the magnetic field was unstable, then it settled here, and again it is moving around. So, if this moves around considerably, then the magnetic field of the earth is unstable, and this unstable magnetic field before actual flip could pose greater danger to life and living, again by producing currents and discharges and so on. So, in this lecture we saw a very important and very interesting, to me at least, topic of Earth's magnetic field, how it varies and how it could reverse, and it has reversed in the past several times. In fact, it has reversed in the past. In next time we continue with magnetism in the next lecture, and we shall study the properties of materials, magnetic properties of materials, and we shall classify them into ferromagnet, paramagnet and diamagnetic materials, and we shall also see some interesting phenomena which is connected with the properties of these materials. In the last lecture, we studied refraction from curved surfaces, which are separating media of refractive indices mu1 and mu2, and we derived this relation mu2 by v minus mu1 by u equal to mu2 minus mu1 by r, which is a relation between the image distance, object distance and the radius of curvature of the surface. And we found that this relation is the same whether the surface is convex towards medium mu1 or it is concave towards medium mu1. And we also see how images formed by such surfaces and how we can trace the rays. At the end, we introduced the basic forms of lenses, and we now continue from that point. This is a double convex lens, and you can see that it can be thought of as being made of several of these pieces, several of these prisms. And you can see that this prism, for example, refracts this ray and this goes this way, and similarly this one goes that way, and this one refracts slightly less than the other one. This one in the middle, which passes through a slab, does not get refracted at all. There is no change in its path. So, we find that in the middle of the lens there is a point through which a ray can pass undeviated. This point is called the optical center of the lens. Please be careful, optical center is not necessarily the center of the lens, geometrical center of the lens. It is any point in the lens through which a ray can pass undeviated. So, while dealing with lenses, we will have several terms like principal axis or optical axis and focal length, distance of the object, distance of the image, and so on. And we shall be dealing with thin lenses. Thin lenses means lenses which are thin, whose width is very small compared with the focal length of the lens. Focal length we shall define more precisely, but you can understand the concept of focal length is the same as in the mirrors. So, we shall assume that the width or the distance between two surfaces of a lens is small, very small compared with the focal length. Such lenses are known as thin lenses, and we shall work in the context of thin lenses. And we shall also take only paraxial rays. Let me remind you, paraxial rays are rays which are near the axis, and they make small angles when they strike the surface of a lens or a mirror. And optical center we have already defined, and let me remind you again, we shall be using Cartesian convention for signs. And here is what all this means. Instead of taking this lens like this, we shall in some diagrams be taking just a line showing that the lenses are very thin, and this is a point inside the lens through which the ray goes undeviated. This is called the optical center of the lens. You can see this is not necessarily in the middle of the lens, and in this diagram we will show it just like this, and this line going through the optical center is called the principal axis of the lens. We are now considering first of all the convex lenses. A convex lens is one whose surfaces are convex, either one or both, or convex towards the medium outside. Okay. So, we will take the convex lens, and for a convex lens, if the rays are parallel to the principal axis and are paraxial, although they do not appear to be paraxial here, but keep this in your mind that the rays we are considering are always paraxial, and these rays after going through the lens meet at the point F, and therefore, F is called the focus of the lens, and the distance OF is called the focal length. All distances are measured from the optical center. So, this is the focal length of the lens, and by our convention, distance measured in the direction of light OF is positive. So, the focal length of a convex lens is positive. If the rays are inclined to the principal axis, they still meet in the focal plane, not at the focal point, but in the focal plane. And once again, let me remind you that the focal length of a convex lens by our convention is positive. The rays emanating from the focus, they become parallel after going through the lens, after passing through the lens, after refraction through the lens, they become parallel to the axis. And similarly, rays emanating from a point in the focal plane also, they become parallel to each other, but not necessarily parallel to the axis. This is another way of understanding the functioning of a lens. You see, this is the focal point and the rays from this after going through the lens become parallel. That means that spherical wave fronts, they become plane wave fronts after the light passes through the lens. Similarly, plane wave fronts, they become spherical wave fronts when the light passes through the lens. I am not sure if you are familiar with wave fronts, but we shall study them later on, these wave fronts. Now, let us take a concave lens. This is a double concave lens. What happens here? The lines, the rays which come parallel to the axis, they diverge. That is why this lens is known as a diverging lens. The convex lens is known as a converging lens, and this concave lens is known as a diverging lens because the rays diverge and they appear to come from this point f. So, this O f is the focal length of the concave lens, and you can see from our convention that this O f is negative. So, the focal length of a concave lens is negative. To find how the image is formed by the two surfaces, let us see the role of each surface one by one. We have this object at A, this is the ray O q, it meets the first surface, gets refracted, and if the second surface were not there, then this would go to I 1. But since this second surface is there, it suffers another refraction and comes to I. We can say that for the second surface, I 1 acts as the virtual object and I is the image formed by the second surface. So, this is how we understand the image formation by a lens. A ray like A q strikes the first spherical surface at q, where it is refracted in the direction q s in accordance with the laws of refraction. If there were no second spherical surface, this would meet at I 1, as I have been saying. However, at S it suffers another refraction and goes to I, and I 1 can be considered as the virtual object for the second surface. And the distance from O of A is u, the object distance. Distance of I from O is v, the image distance. Okay? And keep that in mind. Let us break the process of image formation by a convex lens into two parts, one part on this surface, another part on that surface. So, the first part is refraction at the first surface. So, this ray gets refracted to this, goes to I 1. R 1 is the radius of curvature of this surface. Phi is this angle, alpha is that angle, as before we have been doing this many times now. So, you must be familiar. Mu 1 is the refractive index outside and mu 2 is the refractive index of the medium inside the lens. And we have derived this relation, if you remember, mu 1 by v. In this case, v is v 1, because we are going to use another surface where this would be the virtual object for that surface. So, we use the name v 1. So, mu 2 by v 1 minus mu 1 by u is equal to mu 2 minus mu 1 by r 1. R 1 is the radius of curvature of this surface. What happens in the second surface? We have this ray q s would have gone to I 1, but because of refraction it goes to I. So, I 1 is the virtual object for this surface, that is v 1 is the virtual object for this surface, and the actual image is formed at I. So, therefore, v is the actual distance of the image from the surface. R 2 is the radius of curvature of this surface. Mu 2 is the refractive index inside and mu 1 is the refractive index outside. So, you can see what happens. We have taken refraction at this surface first and then at this surface second time. And again we have the relation mu 1 I equal to mu 1 r as before, and angle I is alpha plus beta, and angle r is equal to beta plus gamma. So, we substitute these values in terms of the distances, assuming small angles, then we get mu 2 by 1 by V 1 plus mu 2 into 1 by R 2 equal to mu 1 into 1 by R 2 plus 1 by V. And if we apply the sign convention, then it becomes mu 2 by V 1 minus mu 2 by V mu 1 by V equal to mu 2 minus mu 1 by R 2. This is the relation for the second surface. So, we can add the two and we get this relation 1 by V minus 1 by U is equal to mu 2 minus mu 1 by mu 1, and this gives us 1 by R 1 minus 1 by R 2. This is known as Lensmaker's formula, and this we got by using this equation and this equation which we have derived earlier. So, from these two equations we get the relation 1 by V minus 1 by U is equal to mu 2 minus mu 1 by mu 1 into 1 by R 1 minus 1 by R 2. R 1 and R 2 are the radii of curvature of the two surfaces. Mu 1 is the medium outside the lens, mu 2 is the medium inside the lens. If medium inside the lens is mu and medium outside is air whose refractive index is 1, then it simply becomes mu minus 1 into 1 by R 1 minus 1 by R 2. This is known as Lensmaker's formula. Why? Because a lens maker has to grind the lens for a given focal length. So, he must know what the two radii of curvature should be given the refractive indices and so on. So, this is known as Lensmaker's formula, and 1 by V minus 1 by U is 1 by F. So, 1 by F is equal to this mu 2 minus mu 1 by mu 1 into 1 by R 1 minus 1 by R 2, and this we can get easily. You see, if we take the object to infinity, this becomes 0. So, this becomes 1 by F. So, 1 by F is this, and therefore, 1 by V minus 1 by U is equal to 1 by F. We shall use that later as the lens equation, but from this equation, by taking U to go to infinity, so that V becomes F, we get 1 by F is equal to this, and this is the lens formula. That is the lens maker's formula, which is in terms of the radii of curvature and refractive indices, and this is the lens formula in terms of V, U and F. In applying this, of course, we shall have to use proper signs for V, U and F in accordance with our convention, Cartesian convention. Now, if the focal length of a lens is expressed in meters, then 1 by F is called the power of the lens. For example, if the focal length of the lens is, let us say, 10 centimeters, that is its 0.1 meter, its power is therefore 1 by F, 1 by 0.1, that is 10, and the unit for power is diopters. So, it is 10 diopters. If the focal length is 20, then that is 20 by 100 meters, that is 0.2 meters, then the power is 5 diopters. If the focal length is 100 centimeters, then power is 1 diopter. So, power is 1 by F, where F is expressed in meters. That is the power that your optician uses for making glasses. And if the focal length is negative, as in the case of a concave lens, then the power is negative. It is 1 by F expressed F when expressed when F is expressed in meters, and the sign it carries, whether positive or negative. All right, let us look at the ray diagrams for lenses. This is the object here, and in fact, we can draw many rays, infinite rays from this, but as we shall see, only 2 would suffice. But let us take the tip. From the tip we draw a ray through F, and after passing through the lens, this becomes parallel to the principal axis. From the tip we draw a ray parallel to the axis, which must pass through the focus on the other side, and we can draw a ray through the optical center, and this ray is not deviated. Wherever these 3 rays meet, that is the image of this point. So, this tip is the image of this tip here. As you can see, we do not need actually 3 rays, we can draw any 2 rays, and wherever they meet in the case of convex lens or where they appear to meet, that is the image of the object. If the image is inverted, it is a real image. If the image is erect, we shall see that is a virtual image. You see, as I have been saying, we can draw infinite rays through all these points which pass through the lens. So, even if a part of the lens is blocked, we still have rays which pass through the unblocked part and form the image. So, if a lens is broken, for example, half of it is broken, does not matter, we can still form an image. This will still act as a lens. The only difference would be the image would not be as bright as it is with the full lens. Why? Because some of the rays have been cut off from reaching this point, and therefore, some of the light that would have gone to this point cannot go because the lens is blocked or broken. Therefore, the image is fainter than the image formed by a complete lens, but it can still function as a lens. Now, let us take the case where the rays appear to meet. In the case of convex lens, let us say this. What happens? We have an object between O and F. O is optical center, F is the focus point, and 2 F is twice the focal length. So, we take two rays, one going through F, which is undeviated. So, it goes like this, one parallel to the principal axis, which must go through the focus on the other side. So, these are the two rays. These two rays are diverging, they will not meet on this side, but when they are taken backwards, when they are extended backwards, they would meet at this point. So, therefore, this tip is the image of this tip, and this foot is the image of this foot. Therefore, this is the image of this object. You can see that the rays appear to meet, they do not meet. Therefore, this is a virtual image, and this is erect, and this is magnified. Now, let us see how the image changes position when object is moved this way or that way. When the object is at infinity, the image is formed at F. When the object is between 2 F and infinity, you can see by drawing the ray diagrams that image is formed between F and 2 F. When the object is exactly at 2 F, the image is also formed exactly at 2 F, and in this case as well as this case as well as this case, the images are real. They can be obtained on a screen. There the rays actually meet. We will continue with this study in the next lecture, and we shall use, and we shall in fact do many examples also of the lens formula 1 by V minus 1 by U equal to 1 by F, which we shall redraw in fact by some other considerations. Here you remember we drew this formula, derived this formula how by considering refraction at this surface and refraction at this surfaces. Now, we shall take the lens to be a thin device and see by trigonometrical means, by comparing triangles and so on, we shall find this relation once again. And we shall also show that if two lenses are placed next to each other, then the focal length of the combination is equal to 1 by f1 plus 1 by f2. In your spectacles, these lenses are almost touching the eye lens, they are in contact, and therefore, the focal length, the power, you can see the powers are added. This is power, this is power, this is power, these powers are added. So, the powers of the two lenses, this lens and the lens of the eye, they get added. And we shall also see the devices like telescopes and microscopes. In the last lecture, we defined many quantities associated with lenses. These are the principal axis, the optical center, focal point, focal plane, etc. Remember that optical center is a point inside the lens through which any ray can pass undeviated. Optical center, as I emphasized in the last lecture, is not necessarily the geometrical center of the lens. It can be anywhere, but it is such that any ray through this goes undeviated. Then we had formation of images. We considered refraction at two surfaces and then combined the result of the refraction at these two surfaces, and we got the formula called lens maker's formula, which is this 1 by f equal to mu 2 minus mu 1 by mu 1 into 1 by r 1 minus 1 by r 2. And we also learned how to draw ray diagrams for images from objects. So, we will continue with this because we have still to cover a lot of ground in lenses. So, we will continue. Remember that if I showed you that if the object is at infinity, the image is formed at the focal point. It is a real image. If the object is between 2f and infinity, then the image is formed between f and 2f. It is again real image, but diminished in size. If the object is at 2f, then the image is also at 2f and is of the same size, real image. Up to that we had done in the last lecture. So, let us continue from that. So, the object now is being moved towards the lens. It is now between f and 2f, and you can form the image as we explained in the last lecture, and we find that the image is formed beyond 2f. It is real, but it is magnified, and when the object is at f, then the image is formed at infinity. So, as the object moves from infinity to the lens up to the focus, the image goes away from the lens. At infinity, it is at the focal point. At 2f, it is at 2f. When the object is between f and 2f, it is beyond 2f, and its size also increases as it goes away from the lens. So, that part we have seen. Now, there is just last position for the object, that is when it is between the optical center and the focal point, that is its distance from the lens is less or smaller than the focal length. So, again I have explained this already in the last lecture, but let me explain it again. We have a ray going parallel to the axis and must go through the focal point on the other side. We have a ray going through the optical center, goes undeviated, and these two are diverging, and therefore, they appear to meet at this point, and this is the image of this object. So, when the object is between the optical center and the focal point, the image is magnified, it is virtual, and it is erect. That is why these lenses are used by older people as reading glasses, for example. You know, people, you have a newspaper where the print is small. So, if you have a convex lens and you place it suitably, you see larger print and you can read it. So, that is the reason behind these lenses being reading glasses. Now, let us find the lens formula by using the geometry. Earlier, we found the lens formula by using refraction at the two surfaces. Now, forget about refraction, we use these triangles. It is much simpler. You see, this is the object, this is the image formed in the usual way. So, we compare these triangles. This A dash is the object, I dash is the image. So, we compare this triangle O A dash and O I dash. These are similar triangles, and therefore, A dash by I dash is equal to O A by O I. So, O A by O I, O A is the distance of the object and O I is the distance of the image from the lens. At the moment, we are not considering their signs, we are considering only magnitudes. Now, we compare the other set of triangles. What are those triangles? These two triangles, and remember that this is equal to that. So, again these are similar triangles, and this by this, that is A dash by I dash is equal to O f, this by this is O f by F I, and O f is of course f, and F I is V minus f, V minus f, this is this. So, O f by F I is f by V minus f, and this is the same as u by v. So, we have u by v equal to f by v minus f, and now you can use mathematics and you can get this relation 1 by v plus 1 by u equal to 1 by f. So far, we have not used any sign convention, we have used only pure magnitudes. Now is the time to use sign convention. According to this sign convention, of course, f is positive. We have seen that for a convex lens f is positive. U being measured in the direction opposite to light is negative, v is positive. So, u is negative, therefore, it becomes 1 by v minus 1 by u equal to 1 by f. So, finally, we get this relation 1 by v minus 1 by u equal to 1 by f. The lens formula is valid in all situations, including the situation when the object is between the lens and the focus, and the image is virtual, erect and enlarged. So, whatever the type of image, the formula is always valid. And magnification we defined as earlier in the case of mirrors. Magnification, magnitude of the magnification is h I by h o. The sign of m is determined by the sign of h I and h o. For a real image, the two are in the opposite direction, and therefore, h I by h o is negative. So, therefore, magnification for a real image is negative. This is upwards, this is downwards. So, for a real image, the magnification carries a minus sign. For a virtual image, here they are on this in the same direction, and therefore, they are the magnification therefore is real, is positive. So, in terms of magnitudes, therefore, you can compare again these triangles. So, this by this is simply v by u, right. So, magnification in terms of magnitudes is h I by h o, the absolute value, v by u also absolute value. We shall find signs depending upon v and u and h I and h o. So, let us fix now the ideas, say whatever we have done, let us see the how to use that information. Consider a convex lens of focal length 10 centimeters. Suppose that an object is placed at a distance of 20 centimeters in front of the lens. Where would the image be formed and what would be its nature? It is a very simple problem, just to illustrate what we have done. So, this is the distance of the object u, this is the distance of the image, and this is the focal length f. And just to remind you, I have made a very thin lens, just to remind you that we are using a thin lens approximation. A thin lens, let me remind you now, is one whose width or whose distance between the two surfaces is much smaller than the focal length. So, we have got this u is there, v is there, and we have to find f. We are given, what is given? Given is the focal length, and so we are given f and u. So, we use the lens formula 1 by v equal to 1 by f minus 1 by u, and we can, why 1 by u? Because the actual formula is 1 by v minus 1 by u, but since u is negative, therefore, it becomes 1 by v plus 1 by u equal to 1 by f. We take 1 by u on the other side, and this becomes 1 by v equal to 1 by f minus 1 by u. Now, you substitute the values of f and u given, and therefore, we can find v, and v turns out to be plus 20 centimeters, showing that the image is on the other side of the lens. Object is here, image is on the other side of the lens, and this v is positive, means that the image is here and image is real, and it is size will depend upon v and u, but image is real. Take another example. Suppose a lens forms a real image at a distance of 30 centimeters from an object placed at a distance of 15 centimeters in front of a convex lens. What is the focal length of the lens? So, we are given u, which is minus in this case, because u is always towards the right of the lens. So, u is minus 15, v is a real image. So, at 30 centimeters, so v is positive. So, v is plus 30 centimeters, and now 1 by v minus 1 by u we can easily find, and f turns out to be plus 10 centimeters, showing that this lens is a convex lens. And if the sign had been wrong, then you must think that there is something wrong. You must suspect something that you have done. If it carries a plus sign, then you are satisfied that this is right, because the focal length of a convex lens is positive. Now, all the work that we have done could have been done graphically. What is that? We have plotted here the image distance, that is v, against the object distance, and the curve is like this from the relation 1 by v minus 1 by u equal to 1 by f, or 1 by v equal to 1 by f plus 1 by u. So, from that curve we have drawn this. This is the curve, and now this is for a particular focal length 10 centimeters. And now you can see that at this point, if this is the object distance, this is u, then this is v. Here, if this is v, then this is the object distance. So, you can use the this graph. For example, if we are given that v is 80 centimeters, then we draw a line parallel to the axis and then draw a line perpendicular to the axis, and we can find the object distance. So, this graph can do everything that we have been doing mathematically. For the sake of your knowledge, this is the graph of 1 by v against 1 by u. This is y equal to mx plus c, the familiar straight line. So, this is a graph, and the slope will give us the focal length. Now, let us take another case. Here the lenses are in contact. So, consider two convex lenses, each a focal length 10 centimeters, placed side by side touching each other. They are in contact. Parallel rays fall on the combination. Where would the image be formed? So, we have parallel rays coming. Where would the image be formed? So, if the second lens is absent, what will happen? The image would be formed at A, where OA is the focal length of the first lens. Now, since there is a second lens, this image at A acts as an object for the second lens, and the final image is formed at B. To calculate the distance of B, let me remind you, is this point. We take this as the object distance for the second lens, and this we will find object distance. The focal length of the second lens is known as 10 centimeters. So, the distance of the image from the lens, second lens, is 1 by v equal to 1 by f plus 1 by u. Why is u? Because 1 by v minus 1 by u is 1 by f. Therefore, 1 by v is 1 by f plus 1 by u, that is 1 by 10 plus 1 by 10. This is 10 centimeters, and the focal length of this lens is also 10 centimeters, and this is positive. Therefore, 1 by v minus 1 by u remains the same, and u on the other side becomes 1 by u plus. So, 1 by 10 plus 1 by 10 is 1 by 5. So, the combination of two thin lenses acts as a single lens of focal length equal to this, because the rays are parallel, and after going through the combination meet at this point B. Therefore, this distance is the focal length of the combination. So, this 5 centimeters is the focal length of the combination of two lenses of focal length 10 centimeters each. And if you consider the powers, what is happening? The powers have been added. The power of one was 10 diopters, 10 centimeters is 0.1 of a meter, therefore, power is 10 diopters. So, the powers of 2 were 10 plus 10, 20 diopters, that is the focal length of the combination is 5 centimeters, because 5 centimeters is 0.05 of a meter, and therefore 20 diopters. So, you convert 20 diopters into focal length, and that is 5 centimeters. We can also prove this mathematically. We can write for the first one 1 by V 1 minus 1 by u equal to 1 by f 1. F 1 is the focal length of the first lens. V 1 is the distance of the image for the first lens, which will act as an object for the second lens. So, 1 by V 1 minus 1 by u is 1 by f 1. For the second lens, 1 by V minus V, now for the second lens this u is V 1. So, therefore, 1 by V minus 1 by V 1 equal to 1 by f 2. So, you add the two equations, this gets cancelled, and you will get 1 by V minus 1 by u would be equal to 1 by f 1 plus 1 by f 2. So, this V 1 is this. So, V 1 is the image of the formed by the first lens, which acts as the object for the second lens. So, 1 by V minus 1 by V 1, you add these two and you will get this relation, and this also means that the powers of the two lenses, they get added. If one is minus and the other is plus, then of course, you get the difference of the two powers. Suppose two convex lenses of focal length 10 centimeters each are placed 31 centimeters apart. An object is placed at 110 centimeters in front of the first lens. Where would the final image be formed? Now, we have two lenses not in touch, not in contact, but separate. So, this is the situation. We have two lenses, the distance between them is 31 centimeters, and the distance of the object is 110 centimeters. The focal length of these two lenses is given. The focal length is 10 centimeters each. So, this is focal length of this is 10 centimeters, the focal length of this is also 10 centimeters. So, what do? We first form the image for the first lens, which is formed here, and then this becomes the object for this lens, and its image is formed here. So, the image of this object is formed here by this combination of two lenses, which are placed at a certain distance. So, what is the solution? U is equal to minus 110 centimeters. It is on the left side of the lens, it is in the direction opposite to the coming light. Therefore, u is minus 110 centimeters, f is plus, because the lens is convex, plus 10 centimeters, and from this you can find v. V is 11 centimeters. So, it is 11 centimeters. That means, this distance is 20 centimeters, total is 31, this is 11, this is 20. Now, for the second lens, the distance is 20 centimeters for the object, which is twice the focal length, and therefore, the image would also be formed at twice the focal length. So, 20 centimeters from the second lens. So, that is the explanation. Since 20 centimeters equals 2 f, the final image will be formed at 2 f or 20 centimeters behind the second lens. Take another example. Two convex lenses of focal length 20 centimeters each are placed 37 centimeters apart. If an object is placed at 100 centimeters in front of the first one, where is the final image formed? See, let me show you the situation. In all these cases, we use the image formed by the first lens as the object for the second lens. The image for the first lens is formed here. We can find this distance. This is 7 centimeters, and therefore, this is 30 centimeters. So, for the second lens, the object is at a distance of 30 centimeters, okay, and you can see where the image would be formed. U is minus 100 centimeters. The image by it is formed at V 1, given by 1 by V 1 equal to 1 by 20 minus 1 by 100, or V 1 is 25 centimeters. So, this is at 25 centimeters. Okay. So, that means, this leaves only 12 centimeters. So, the distance between the object and the second lens is 12 centimeters. Its focal length is 20 centimeters. It is less than the focal length. Therefore, the image formed by the second lens would be virtual and erect. So, you can calculate with 12 centimeters and 20 centimeters as focal length, you can see where the image would be formed. It is at, for this lens, minus 30 centimeters. So, this is therefore an image which is virtual. So, these two lenses form the virtual image. The first image is formed here, the second by this lens is formed here. That is how we proceed. Even in the earlier case, you remember, the first lens forms the image here, and then this becomes the object for the second lens, and we can calculate where the image would be formed. Whenever we have combination of lenses, we proceed like this. First lens, we find where the image is formed, this acts as the object for the second lens, here as well as in this example. First image is formed here, this becomes now the object for this lens, and therefore, the image we can calculate is formed here at 30 centimeters from this lens. Now, these two examples, the ones that we have done, we have taken two lenses in each case. This tell us that we can arrange lenses and we can get the image anywhere we like. So, this is the principle behind microscopes and telescopes, that you can arrange lenses in such a way that you can get the image either magnified or diminished or virtual or real by just arranging the position of the two lenses. That is the principle behind telescopes and microscopes. So, these examples tell us that by arranging lenses suitably, it is possible to cast the image of an object at any desired location and also control its nature and magnification. This is the principle underlying the construction of telescopes and microscopes. Telescopes are used to bring distant objects close to the eye. For example, stars or planets or very distant objects, they become closer to your eye, as we shall show here, right, and therefore, we can see them better. Their magnification therefore, will also be measured in terms of the angle that the object subtends at the lens and at your eye. So, this is the ray diagram for a telescope, a simple telescope. We have a lens here called objective, and the rays from a distant object, they are parallel and they meet at a point in the focal plane. Okay. And this is a smaller lens called eyepiece, and this point is such that it is in the focal plane of this lens also. So, the rays are rendered parallel and they enter the eye. This lens is called eyepiece, this lens is called the objective lens, and this is the focal length of the objective, and this is the focal length of the eyepiece. And the magnification you can see, we will calculate in a moment, is f0 by fe, is the ratio of the focal length of the objective and the focal length of the eyepiece. And this is calculated, in fact, if this h is the size of the image, then h by fe is where h is the size of the image, this is the angle, h by fe is the angle, this angle is subtended at the eye, and this angle is much larger than this angle, h by fo. This angle is much smaller than this angle, although it does not appear from this diagram, but in actual fact this angle is much larger than this. Therefore, we always call angular magnification of the telescope, and this angular magnification is f0 by f objective by f eyepiece. And therefore, by increasing the focal length of the objective and by decreasing the focal length of the eyepiece, we can get a large magnification. So, the requirement to maximize magnification is thus to have an objective of very large focal length and an eyepiece of very small focal length. Moreover, in order to gather more light from the objective must have a large diameter. See, light is entering through this, and therefore, this must have a very large diameter, so that more light can enter. And these days we have huge lenses, in fact, through which the light can pass, and they gather much more light than smaller lenses. The convex lenses satisfying these two requirements, that is large focal length for magnification and large size for getting more light. These twin requirements make the lens very heavy, and therefore, modern telescopes do not use these lenses, they use mirrors, as I shall show you in the next lecture. In the next lecture, we will continue this discussion of the telescopes and see that why we use the concave mirrors instead of the convex lenses. And we shall also learn about the resolving power of an optical instrument, which is proportional to the wavelength used and inversely proportional to the diameter of the objective lens. And we shall also learn in greater detail the advantages of reflecting telescopes over refracting telescopes, and we shall also have ray diagrams of microscopes. We shall find the magnification of a microscope, and then we shall go on to concave lenses. So far we have not discussed concave lenses. We shall go on to concave lenses and derive this lens formula, which is the same as for the convex lens.
Hello viewers, continuing with our series on continuity and differentiability, today we are going to discuss two special techniques of differentiation, one called logarithmic differentiation and the other which would help us to differentiate functions which are in the parametric form. Let us start with looking at some functions which you may not have come across earlier as in the methods of differentiation. Let us consider functions of the kind x to the power x, cos x raised to the power x, log of x raised to the power tan x. These are special class of functions which in general can be expressed as a function of x raised to the power a function of x. So far we have not learned any method of finding derivatives of such functions. And just in case you are thinking about using the formula x to the power n to differentiate x to the power x, then stop and understand that that formula, that is the derivative of x to the power n is n x to the power n minus 1, is applicable only if n is a constant, is any real number. In this case, the power is also a function of x. So, here we use logarithm to the base e to differentiate such functions. Now, what do you know about logarithmic functions? Let us just catch up with that. Logarithmic functions are defined for any b greater than 1 as functions which are defined on positive real numbers to the real numbers, and the rule is y results in log of x to the base b if b raised to the power y is same as x. So, there is definitely a relation between exponential functions and logarithmic functions. If you had spent a little more time on this, you would have recognized that they are inverse functions of each other. Along with that, there are several useful properties of logarithm which we will be using as we progress down to this method. These are very essential and these are the key to the process which is known as the logarithmic differentiation. So, do make a note of them. Along with that, what we also need is an understanding of what are the derivatives of log and exponential functions. So, here are results which are mentioned just directly without proofs in your textbooks as well, which says that the derivative of exponential function is exponential x, derivative of log x and when I write log x as v, that is the mathematicians do, it is meant to be with the base e. So, derivative of log x is 1 by x, derivative of a raised to the power x is a to the power x log of a, and derivative of log x to any other base other than e. So, in this case base a is same as 1 by x times log a. These 4 results will of course play a role as we go along and use the derivatives of logarithmic functions and exponentials anywhere else as well. Let us demonstrate to you the method, the process which is known as logarithmic differentiation through a simple problem. Starting with find dy by dx if y is equal to log of x raised to the power tan x. So, we begin of course with our function which is y is equal to log of x raised to the power tan x. In order to make it possible for us to differentiate, we take logarithm, and of course again I am emphasizing to the base e of both sides. So, I get log of y is equal to log of log x raised to the power tan x. This gets rewritten as tan x into log of log x. How? Again, if you had noticed, this was one of the properties listed in our earlier slide. Here we have log of p to the power n is equal to n times log p. This helps us to bring the power as a factor in this expression, and therefore, we are now ready to differentiate both sides with respect to x. I get the derivative of log of y with respect to x, derivative of tan x into log of log x. This needs to be looked at with care, that when you differentiate log of y, there is a presence of chain rule, because log y is composition of logarithmic function and y which is a function of x, whereas the right hand side is product of two functions. So, to differentiate the right hand side, you need the product rule, and therefore, what would be the derivative of log y 1 by y into dy by dx, whereas the right hand side will result as the application of product rule applied on tan x and log of log x. So, we get on differentiating 1 by y dy by dx equal to sec square x log of log x plus tan x, and note how we have differentiated log of log x. Again presence of chain rule, log derivative will give me 1 by log x. So, when I say log derivative, it is derivative of log x with respect to log x, and then chain rule requires that I multiply with the derivative of log x, which is 1 by x, and thus our dy by dx is ready. Taking y to the right hand side, I get log of x raised to the power tan x into sec square x log of log x plus tan x into 1 by x log x. Not much gets simplified in this case. So, obviously, we would not worry too much about the simplification. Let us take another question, and this is one of the very frequently tested question in the class 12 board exams. The question says find the derivative, that is dy by dx, where y is x to the power sin x plus cos x raised to the power x. Now, you can see that it is just the first question that we did earlier repeated almost twice, because both the terms are of the class where we have f of x raised to the power g of x. So, both the functions need log in order to get the differentiation done. But also remember that there is no rule which says that log of the sum is same as sum of the logs. So, what can one do? Simply start with u as x raised to the power sin x and v as cos of x raised to power x. Then your y becomes u plus v and dy by dx is du by dx plus dv by dx. That is exactly what we did in our previous question. So, I will leave this for you to complete yourself. Repeat the same process mechanically and you will be fine. Consider another application. Find dy by dx if y is equal to this big expression where we have a square root, I have a quotient and I have product in both numerator and denominator. A usual chain quotient product rule procedure will make the task quite tedious. So, this is another situation where we take help of log and its properties which help us rewrite this function, simplify it down and then we bring in differentiation. Starting with y, which is square root of x plus 1 into x minus 3 upon x minus 4 into 7 minus x into x plus 2. Taking log of both sides, we get log of y as log of the entire expression, and again using the properties that we have just displayed, it all simplifies to half of log of x plus 1 plus log x minus 3 and then minus, because now we are looking at log of m by n resulting in log m minus log n. So, the entire expression gets written either as the sum or difference of terms which are with log. Taking the derivative, I get 1 by y dy by dx is equal to half times of 1 by x plus 1 plus 1 by x minus 3 minus 1 by x minus 4 plus 1 by 7 minus x. Now, where did I get this plus from? Because I had log of 7 minus x. So, when I take the derivative, it will be 1 by 7 minus x into the coefficient of x, which is minus 1, and therefore, I get a positive sign there, minus 1 by x plus 2 as the derivative of log x minus 2, and your problem is done. You just have to now rewrite your dy by dx by transposing y to the other side and just complete by saying what that y was. So, this is one more application of using the log to find the derivative of a function, process known as logarithmic differentiation. Let us also consider something new which you have again not come across earlier. Functions which are in the parametric form. The functions which are in parametric form represents the equation of a curve by a pair of equations, where these pair of equation represents the coordinates of the point on the curve in terms of a certain parameter. In this case, for example, if I have x as cos t, y is equal to sin t. This represents nothing but parametric equation of a circle with radius 1. You do not believe that? Well, it is so. You are familiar definitely with x square plus y square equal to 1 as the Cartesian equation of a circle with unit radius. So, if you do square x and y and add cos square t plus sin square t is equal to 1. So, t changes and it generates the coordinates of the points which lie on the curve, and that is a way of representing a Cartesian equation in terms of parameter. We are interested in finding the derivative of y with respect to x, where both x and y are functions of a certain parameter, say t. Then in that case, dy by dx is nothing but dy by dt divided by derivative of x with respect to t. So, as t changes, we find the instantaneous rate of change of y and divide by the instantaneous rate of change of x, provided denominator is not 0. And we are fine to find then the derivatives of functions which are in the parametric form. Consider one application. If x and y are connected parametrically by the equations, x is a times theta minus sin theta, y is a times 1 plus cos theta. Find dy by dx. So, what do? You begin by first finding dx by d theta. So, derivative of a times theta minus sin theta is nothing but a times 1 minus cos theta. Similarly, derivative of y, you have practiced differentiation to a large extent right by now. So, you are expert at finding such derivatives. dy by dx is nothing but the quotient of these two derivatives in the order derivative y with respect to theta divided by derivative of x with respect to theta. One does expect you to simplify this expression a little more. In this case, a gets cancelled. Not only that, trigonometric identities help us to rewrite sin theta as 2 sin theta by 2 cos theta by 2, 1 minus cos theta as 2 sin square theta by 2. It all simplifies to be same as minus of cot theta by 2. That would be the derivative of y with respect to x, where x and y are parametric functions of theta. So, the derivative is also a function of theta, it is not the function of x in this case. So, today's lesson covered two interesting important techniques, one logarithmic differentiation and the other which just touched upon the derivatives of functions in parametric form. I hope this has helped you to clear your doubts. Now, it is up to you to open books, start practicing and get expert at both the methods. See you in our next lesson. Thank you. Hello viewers. English mathematician Isaac Newton and German mathematician Leibniz are usually credited with the invention of calculus. But earlier mathematicians, including several Indian ancient mathematicians, also explored the concepts of rates and limits. Today, calculus has invaded every scientific endeavor. You can find its use in physics, chemistry, biology, economics, sociology, engineering of course. Calculus helps us to understand the structure of a rainbow, teaches us how to make more money at stock market and of course guides a spacecraft. Today, we begin our explorations with application of derivatives, starting with problems of tangents, which puzzled even Isaac Newton and Leibniz in 1600. What does tangents and normals have to do with derivatives? Let us take a look at it through an applet. Here we have a graph of the quadratic function. Let us take a point A on this graph and construct a tangent at the point A. Let us also measure the slope of this tangent. In this position, the slope of the tangent is represented by the number b, which is taking the value 2. Let us also construct a point P which has the coordinates same as the x coordinate of the point A and the slope b as the y coordinate. Note that as I change the position of the point A, the position of the point B also changes. You can see that it is leaving a certain trace behind, and also there is a certain relation between the x coordinates of the point P, which you can see resulting in a certain list on this table that is on the right hand side. Now, I am going to again move the point and you observe and decide what the relation is going to be. So, as you move the point A, these values very quickly change, but you can keep an eye on them and see that there is a certain relation present on the x and the y coordinates of the point P. Can you guess what that relation is? Yes, definitely y is equal to 2x as far as the coordinates of the point P are concerned, and that is exactly what is the derivative of x square, right. So, what does that all mean? What we have just shown is a representation of a fact which has been said again and again, that derivative measures the slope of the tangent to the curve at any point. So, what is derivative of a function? It measures the steepness of the graph, so it is a slope. Also, it is the slope of the tangent line to the graph of the function at the given point, and it is slope of a secant line, that is the line which is connecting 2 points on a graph in its limiting position when it becomes the tangent. So, in the limiting position, when the 2 points come closer to each other, we get the slope of the tangent, which is also what we understand as the derivative. Once this is understood, what we need to figure out is how to find equation of the tangent to the curve at a given point. So, what we have just now discovered is that the slope of the tangent to the curve at the point x1 y1 is the value of the derivative at that point. So, it can be represented as dy by dx at x1 y1 or f dash at x1. So, the equation of the tangent to the curve y equal to fx at the point x1 comma y1 is y minus y1 is equal to dy by dx at x1 y1 into x minus x1, coming off from the simple slope point form of the straight line. Equation of a line is y minus y1 equal to m times x minus x1. Also, we have equation of normal to the curve at a given point. We have the slope of the normal at the point x1 comma y1 to the curve y equal to fx given as minus 1 by dy by dx at x1 y1. Why? Because the normal is perpendicular to the tangent at the point of contact, and therefore, the equation of the normal to the curve is simply y minus y1 equal to negative 1 upon dy by dx at x1 y1 into x minus x1. This is something very straightforward. At the same time, what you need to be careful with is to form equation of a line, in this case tangent, you need two important quantities, the point and the slope of the tangent. Once these two are known, we are ready to face any situation. Here is a simple question to begin with. Find the equation of tangent to the curve y is equal to x cube minus x plus 1 at the point whose x coordinate is 2. So, as I said just now, to begin with you must know the point at which the tangent is to be constructed, that is x1 comma y1. Since it is a point on the curve, when x is 2, y can be calculated by putting the value of x as 2 in the equation of the function. Dy by dx is 3x square minus 1. So, the slope of tangent at 2 comma 7 is nothing but the value of dy by dx at 2 comma 7, resulting in the number 11, and therefore, the equation of the tangent to the curve using the point slope form would be y minus 7 equal to 11 times x minus 2. Simplify, express as a linear equation in the standard form ax plus by equal to c. We have another problem where the information is indirect. Find the equations of the normals to the curve y equal to x cube plus 2x plus 6, which are parallel to the line x plus 14y plus 4 equal to 0. So, what you are given directly or indirectly is the line is such that the normal to the curve is parallel to it. So, slope of line will be same as Slope of normal. You know the slope of normal. What is the second thing that you need? The point of contact. So, our main work would be to get that point of contact through the given information. Starting off with therefore, the unknown, let x1 comma y1 be the point of contact at which the normals to the curve are parallel to the given line, and therefore, the slope of the line, which was minus 1 by 14, will become the slope of normal to the curve at x1 comma y1. Also, we know the slope of the normal is negative reciprocal of the derivative at that point. So, let us find the derivative, which is 3x square plus 2. Therefore, the slope of normal in terms of derivative will be negative 1 by 3x1 square plus 2. Equating the two quantities, what we had and what we have found out, I get a relation in x1 giving me two values of x1, and therefore, there will be two values of y1 since x1 comma y1 lies on this curve. So, I get 2 points at which the condition is being satisfied as 2 comma 18 and negative 2 comma negative 6. So, that is why in the question asks for normals to the curve. There is a plural word here. So, I need two normals. I have two answers for this question. The normal at 2 comma 18 with slope negative 1 by 14 will turn out to be x plus 14y minus 254 equal to 0, and the second normal turns out to be x plus 14y plus 86 equal to 0. Something which was indirect, but we could figure it out because I had a known and an unknown linked together through the concept of normal slope being the negative reciprocal of the derivative of the function. Another question, an important one. One more important question for you. Pay attention to the statement. The question says find the equation of normal to the curve x square equal to 4y which passes through the point 1 comma 2. What is significant and what is risky about this question is the tangent normal are constructed at a point of the curve. So, here the normal is passing through the point. This point is not the point of contact between the normal and the curve. So, you cannot use this directly as your x1 comma y1 and then proceed with finding the derivative at this point. So, that is one important information for you to pay attention to. So, the point of contact is still unknown. Let us begin with that as x1 comma y1. So, if x1 comma y1 is the point of contact, derivative gives me x by 2. Therefore, the slope of normal at x1 comma y1, which is the negative reciprocal of derivative at x1 y1, will be negative 2 by x1. This results in an understanding of slope as a quantity which is still unknown. I have to equate it with something else to get the value of x1. So, what is the other information that we have? The normal passes through the point 1 comma 2 and it also is passing because it is at x1 comma y1. So, I have 2 points through which the normal passes, and therefore, the slope of normal using our 2-point form would be 2 minus y1 upon 1 minus x1. So, I can equate it with negative 2 by x1, but I can make it first a function in one unknown by replacing y1 with x1 square by 4, because x1 square was 4 times y1. x1 y1 lies on the curve x square equal to 4y, right. So, we are ready to simplify and equate with negative 2 by x 1. What is left is simplification. Cross multiply, something simplifies, cancels out, gives you x 1 as 2. Once I have x 1, using again the expression that x 1 square is equal to 4 times y 1, I get y 1 as 1. Therefore, the point at which the normal is constructed has the coordinates 2, 1. Slope of normal, which was negative 2 by x 1, takes the value negative 1. So, I have the point, I have the slope, and therefore, the equation of normal y minus 1 equal to negative 1 times x minus 2. Simplify and express it in the standard form. I get the equation of normal as x plus y equal to 3. So, with this we end today's lesson on tangents and normal. I hope this has helped to clarify some of your doubts. Thank you for watching.
In the last lecture, we were discussing surface tension. In particular, we discussed the angle of contact, and we found that if the angle of contact is less than 90 degrees, it is acute, then the liquid will wet the solid surface. If the angle of contact is more than 90 degrees, then the liquid will not wet the surface of the solid. And this wettability is important from the point of view, say, in our daily lives, from the point of view of cleaning clothes. If the water is not able to wet the surface of clothes, then it will not be able to remove the dirt. So, therefore, we add detergents which reduce surface tension and also reduce the angle of contact, so that the water spreads over the surface and is able to clean the soiled areas. In this lecture, we take some other properties of fluids. We will talk of streamline flow and we will talk of the important Bernoulli's principle. If you have ever stood on the bank of a large river, say like Ganga or Yamuna in plain areas, you will see the water flows very slowly, very placidly, very orderly. There is it's a very orderly flow of water. On the other hand, if you ever stood on the banks of a river far from its source, that is in the plains, say a large river like Ganga or Jamuna, you must have noticed that the water flows very placidly, very quietly and very orderly. If you choose a point, at that point the velocity of flow is constant. Such flow is called streamline flow. On the other hand, if you see stream or a river or water in a channel which is, say, during floods, then you will see that water does not flow quietly, does not flow orderly. There are, let us say, things like these irregularities and these eddies in water. The water does not flow quietly, but it flows like this, and if there is some obstruction, then it flows over it, and there are eddies like this produced in water. And if you concentrate on a point, then at that point the velocity is not constant. Velocity of flow is not constant. The direction of flow is also not constant. It keeps changing every second. Such a flow is not a streamline flow. I will give you an example, very interesting example. If you have visited say some place higher up in Himalayas, you must have seen a river or a stream there. I have a picture of river Ganga in the Himalayas, and you see the water flowing not very quietly, not very orderly, and it has a very sort of, there are eddies if there is an obstruction and so on. This kind of flow is not a streamline flow. The streamline flow is this, where it is very steady, and if you concentrate at a point, then the direction of flow of water and the velocity of flow of water is constant. Now, these are again streamlines. How do you define a streamline? A streamline is shown here, a blue curve, and the tangent to it gives the direction of flow of water. And if a small object, say a piece of wood, is placed into water flowing steadily, the path traced out by the object is called a streamline. That means, if you want to see what a streamline looks like, you stand at the bank of a large canal, say, just float a paper boat, and then you see the direction that it takes. You will see it will flow steadily in the same direction, and the path it traces is called a streamline. And I show streamlines here, and the tangent to a streamline at a point gives the direction of flow of water. Here again two more examples of streamlines. Take this streamline for example. Here the tangent to this is in this direction, so this is the direction of flow. Here the tangent is in this direction, therefore, this is the direction of flow of water. The concept of streamlines is similar to the concept of lines of force in electric field or magnetic field. Let us take an electric field. This is the line of force. Tangent to it gives us the direction of the field. In a streamline, similar thing happens. The tangent to the streamline at a point gives the direction of flow. As two lines of force cannot cross each other, because we must have a unique direction of the field at that point. Similarly, two streamlines also do not cross, because at a given point you cannot have two directions of flow. You must have a unique direction of flow at that point. So, therefore, two streamlines do not cross each other. I show you two more examples of streamlines. Suppose water is flowing and we have a cylindrical object in its path. Then what happens? The water will flow over it, just as here. This is a cylinder and water flows over it orderly in streamlines, if the flow is not at very high speeds. Here is an important thing called aerofoil or airfoil, and if this is in the way of the fluid flow, then the streamlines will take this shape. They will go over it and they will go under it, but they will remain streamlines. The motion of the fluid is said to be turbulent when it is highly unsteady, as I showed you the example of the river Ganga somewhere near its source. You see, here water flows chaotically. I mean, at a given point the direction of flow changes, the velocity of flow changes, and if there is some obstacle, then eddies are produced inside this water. This flow is called turbulent flow, and turbulent flow is very difficult to understand mathematically, at least at this stage. How does turbulent flow come in? Here you have the streamlines, as I showed you earlier also. This is a cylinder, the water flows over it and water flows under it and flows along streamlines. This is slow fluid motion. But suppose the fluid motion becomes fast, then what happens? Then you start seeing these eddies behind the cylinder. You will start seeing these eddies. This is the beginning of the turbulent flow. And if the velocity of the fluid increases more further, then you will see more of such eddies. The turbulent flow has become more turbulent as the velocity increases. What decides whether the flow would be turbulent or streamline? There is a number called Reynolds number, which decides whether the flow would be streamline flow or would be turbulent flow. And this number is given by this expression rho V L by eta. Rho is the density of the fluid, V is the velocity, typical velocity of the fluid, and L typical dimension of the channel in which the flow takes place, and eta is something that I will explain further also, is something called the viscosity of the fluid or viscosity of the liquid, and this number is dimensionless. If you plug in the dimensions of rho, V, L and eta, you will find that this has no dimensions, this is just a pure number. So, this is the streamline flow. In the case of water, this Reynolds number must be less than or about 2000. If this is less than 2000, then the flow is streamline as shown here. There is no turbulence, you can see there are no eddies, there is no irregularity. On the other hand, when the number Reynolds number goes beyond 2000, then flow starts becoming turbulent. I mean, it starts becomes irregular, and when R is greater than about 4000, then the complete turbulence comes about. Water flow is completely turbulent. So, let us see the situations where this R will give us turbulent or streamline flow. First, Reynolds number is a dimensionless number, as I already explained. Less viscous liquid, viscosity of liquid is like resistance, something like resistance, we will explain in a moment. So, less viscous liquids are more likely to become turbulent. You see, eta is in the denominator. So, if eta is smaller, then R increases, that means the possibility of turbulent flow increases. Flow in broad channels is more likely to become turbulent, because the radius or the cross section of the channel is in the numerator. So, if L increases, R tends to increase, and therefore, the probability of flow becoming turbulent is higher. As long as Reynolds number is below about 2000, the flow of water remains streamline flow. What happens if the flow is streamline? You see, when water flows through a channel, say a pipe or a tube, then the attraction between molecules of the substance of the channel and water molecules, and then the interaction between water molecules further off the walls, all this results in the resistance to the flow of water in each layer. So, what happens is that near the wall the resistance is so much that there is almost zero velocity, very small velocity. If you observe this, you will see that water along the walls is flowing very slowly, and this velocity increases and becomes maximum in the middle of the channel. The velocity increases gradually, and the layer along the axis moves fastest. The forces between molecules in adjoining layers of the fluid produce friction between layers of the fluid, which results in the resistance of the fluid to flow. So, the result is that near this wall the flow has very small velocity, near this wall of the tube the flow has very small velocity, and it increases, and obviously along the axis the flow is with the largest velocity. And this resistance to flow, say this layer is being affected by molecules above and below, they cause resistance, and the resistance to flow is called viscosity. Now, since there is a resistance to flow, we must apply a force to make water flow through a pipe or through a tube. Let us look at this picture. As we go away from the wall, then the velocity increases. That means, there is a velocity gradient dV by dy, there is a velocity gradient, and the force that we need to apply to make water flow in a streamline flow through a pipe or a tube is F equal to the area of cross section of the tube into the velocity gradient and into a constant eta. This constant eta is called the coefficient of viscosity of the fluid. This determines the force that needs to be applied to make the flow overcome resistance and flow. From the formula for eta, the units of viscosity are found to be Newton second by meter square or kilogram by meter seconds. There is no special name for any unit in SI system. However, people use a unit called poise, and 1 poise is 1/10 of Newton second per meter square. In addition to eta, we also have what is known as kinematic viscosity, which is eta by rho. You divide by the density, and the viscous flow, where velocity of the fluid increases towards the axis of the pipe or tube, is also known as laminar flow. Flow in, see, like a laminate, this is laminar flow, and I show you again, the flow is streamline, the velocity increases as we go towards the axis. That means the velocity profile has this shape, and the liquid flows through the pipe. This flow, in which the flow is streamline flow, is called laminar flow. Now, suppose we have laminar flow, then what happens? A spherical body of radius r is moving through it with not too large a velocity, I mean with a small velocity. The viscous resistance or viscous drag experienced by it is given by Stokes' law. You see, suppose we have air in this, say a small ball of lead, let us say, is allowed to fall, then this ball will experience resistance of the fluid, in this case air, and this is the force, that force of resistance exerted on this ball is given by Stokes' law, and this force is called drag force, F d equal to 6 pi eta r v, where eta is the familiar viscosity, r is the radius of the ball, and v is the velocity with which the ball is falling in air or in any other liquid. Now, suppose the body is falling in air, neglecting buoyancy due to, you see, if a body falls into a liquid, then there is a force of buoyancy acting upwards. We can neglect, in the case of air, the force of buoyancy. Then the net force acting on the body is its weight mg minus the force which is upwards, which is 6 pi eta r v. So, the net force is 4 pi by 3 pi r cubed rho g. This is the volume times density times g, that is the weight, and 6 pi eta r v, that is the force given by Stokes' law, which opposes the motion of this body. If we equate these two, then the velocity, you see, if these two forces become equal, then there is no force acting on a dropping, say, ball or even raindrop. There is no force acting on it, and therefore, since there is no force, there is no acceleration, therefore, the velocity becomes constant, and this constant velocity is called terminal velocity. You see, you have a raindrop coming from a great height, and then at some stage the weight is balanced by the force of viscosity or force due to viscosity given by Stokes' law. At that point, there is no net force acting on the raindrop, and therefore, it acquires what is known as terminal velocity. After that point, it falls with constant velocity, terminal velocity. And if we just use this formula to derive the expression for V by equating these two, and V terminal is 2 rho g by 9 eta times r squared. Notice that it is proportional to r squared, and we shall see very interesting consequence of this, is proportional to r square. Because of their long journey, raindrops and hails are bigger pieces of water falling, are able to acquire terminal velocity. Then they fall with constant velocity. Since the terminal velocity is proportional to r squared, larger and heavier hail pieces, they fall faster. Remember, according to Newton's law, every object must fall with the same acceleration. Here we find something different. The larger pieces fall faster than the smaller pieces. It is all because of viscosity, and these larger pieces, they acquire larger velocity, larger kinetic energy when they suppose hit you, and therefore, they can cause greater damage. So, if you are going outside in rain, and rain drops will not harm you, but if there is a hailstorm, hails falling can cause lot of injury, because hails being larger in size, they acquire larger terminal velocity and larger kinetic energy, because the terminal velocity is proportional to r square, and therefore, these hail pieces they fall faster than the smaller and lighter ones, making them potentially more dangerous if they hit you. When a body falls in a liquid, say a steel ball falling in a liquid column, then force of buoyancy cannot be neglected. Then what happens is, the drag force as well as the force of buoyancy, they act upwards, the weight of the ball acts downwards, and when these two are equal, the upward force and the downward force, then the ball acquires terminal velocity. And the equation now is this: the F net, the net force acting on the ball is 4/3 pi r cubed into g into rho b minus rho l. Rho b is the density of the ball, rho l is the density of the fluid, and this 4/3 pi r cubed rho l into g gives the force of buoyancy. This is equal to the weight of the liquid displaced, and this is the weight of the ball itself, and this is the Stokes law, the force due to the viscous drag. And when F net is 0, then we get the terminal velocity, and the expression now is 2 r squared into g by 9 times eta into rho b minus rho l. So, if you have a small ball of steel falling in a long column of mercury, say in a burette, then you can see that it falls, it has an acceleration, but after some time it falls with constant velocity, because the net force acting on it becomes 0, and after that the velocity becomes constant. In this lecture, we have discussed some properties of fluid, like the viscosity, streamline flow, turbulent flow, and the terminal velocity which is acquired when a particle falls through a long column of a liquid. Next time, we shall take some more properties of liquids. We shall discuss Bernoulli's theorem. We shall also discuss Torricelli's law and some other phenomena. In the last lecture, we were discussing the properties of fluids. In particular, we discussed the streamline flow and the turbulent motion of the fluid. We also discussed the viscous drag that an object feels when it moves through a fluid. Today, in this lecture, we continue with fluid properties, and we shall discuss two very important topics: Bernoulli theorem and Torricelli law. So, we start with this discussion. The fluid is going through a tube of cross section A. Then how much fluid goes out or enters in this tube per second? So, to do this, we choose a length equal to the speed of the fluid, length v, so that the volume of this element is A times v, and the mass of fluid in this element is rho times A times v, rho, A and v. And in 1 second, since the velocity is v, in 1 second all this matter, all this fluid will come out. So, every second the fluid that comes out is rho A V. Now, suppose we have a variable cross section A 1 here and cross section A 2 here. The fluid entering per second in this rho A 1 V 1 and going out through this cross section is rho A 2 V 2, and rho is common. Therefore, A 1 V 1 is equal to A 2 V 2. So, why is it so? Because on the way there is no point where the fluid accumulates. Whatever enters goes out. Therefore, this is known as the equation of continuity of mass. Rho A 1 V 1 is equal to rho A 2 V 2, rho being common, A 1 V 1 equal to A 2 V 2. Now, along with this mass continuity, we also need an equation which tells us about energy continuity or energy conservation. So, for this purpose, we make these assumptions that the flow is streamline. You would recall what a streamline flow is. So, we assume that the flow is streamline. We also assume that fluid has negligible viscosity, what is known as inviscid fluid. Viscosity is very small and fluid is incompressible. We make these three assumptions and then we take this streamline flow. Let me explain this diagram. Here is a cross section A 1 and the cross section here is A 2. The pressure which pushes the fluid in is P 1, the speed is V 1, and from a standard or reference line the height of this fluid element is H 1. Here these quantities are A 2, P 2, V 2, H 2. This fluid is moving and after some time this element finds itself here, and then let us see what happens. This element finds itself here. Since the volume remains constant, therefore, A 1 L 1, A is the cross section here, A 1 L 1 is equal to A 2 L 2, because A 2 is the cross section here. This volume is equal to this, and this is V. Now, the pressure difference is P 2 minus P 1. Therefore, the work done in moving this volume V would be P 2 minus P 1 times V. The work done is P 2 minus P 1 times V, but per unit volume the work done is P 2 minus P 1. The gain in kinetic energy, you see there is the tube narrows down and therefore, the velocity increases, and therefore, the gain in kinetic energy per unit volume is half rho V 2 square minus V 1 squared, and the gain per unit volume in potential energy is rho g times H 2 minus H 1. So, if we equate the gain in energy with the work done in pushing the fluid through the tube, we get this equation. P 1 by rho plus half V 1 squared plus G H 1 is P 2 by rho half V 2 squared plus G H 2, means that this quantity P plus half V squared plus G H remains constant along a streamline. Now, this is all energy, half V squared G H and per unit volume, this is all energy. So, this is the equation of energy conservation as the fluid moves along the streamlines. Usually, there is not much change in potential energy, not much change in height. Therefore, the last term G H can be dropped, and then we have P plus half V squared plus G H remains constant along a streamline, and as I said, since there is not much change in potential energy, therefore, G H can be dropped, and we have P plus half V squared constant along a streamline. That means what? That if V increases, P has to decrease, or if V decreases, P has to increase. So, along a streamline, as the fluid moves, if velocity becomes very large, pressure becomes very small, or vice versa. Let us see what is the effect of this. This theorem is called Bernoulli's theorem, that P plus half V squared plus G H remains constant along a streamline is known as Bernoulli's theorem, and let us see what the effect of this is. Imagine a house. Suppose very high velocity wind is flowing along the roof of this house. What happens? The pressure on the outside of the house decreases. Why? Because high speed wind is moving. So, the pressure here is less, the pressure inside is high. Therefore, sometimes the pressure inside and pressure outside, the difference is so much that a whole roof can be blown away. This happens especially in wind storms, high velocity wind storms. I shall show you two photographs. This damage caused becomes very severe during cyclones and tornadoes when very high velocity wind flow. Please notice especially how the roofs have been blown away. The high speed wind is accompanied by a very low pressure, and the pressure from inside blows away the roof. This can cause lot of damage. Here I show you illustrate the Bernoulli's theorem. The fluid is moving, here the speed is high, but the pressure is low. Here the speed is low, but the pressure is high. So, wherever speed increases, the pressure decreases, wherever speed decreases, pressure increases. That is the content of Bernoulli's theorem. Another application of this Bernoulli's theorem is in the lifting of airfoil. Airfoil, I told you in the last lecture, is a specially shaped object, and the streamlines go as shown here, some over and some under this. Speed is high in this region, in the upper region above this airfoil. Then what happens? If the speed is high, the pressure becomes low, and the high pressure from below pushes the airfoil up. There is an upward lift, and this is what we make use of in aeroplanes. Here is a drawing of an aeroplane, may not be very impressive, but this is an aeroplane, and you can see what is happening. There is a high speed wind and low pressure on the upper side, and low speed and high pressure in the lower side, and the high pressure from the lower side pushes this plane up. That is how the planes fly in simple terms. There are quite a few classroom activities to illustrate Bernoulli's theorem. A few are given in class 7 science book of NCERT. In addition, we give two more examples here, two more activities here. Make a paper tent as shown. I mean, you take a piece of paper and make it as a tent and put it on a flat surface, and you below the tent, you blow in this space below the tent. What happens? As you blow, the high speed wind goes through and the pressure decreases, and the pressure outside makes it collapse. So, this tent will collapse. Take another interesting activity. Take a shallow cup and put a small ping pong ball in that egg stand or a shallow cup, and place it on a table, let us say, and you blow over the cup, and you would see that the ball gets lifted and floats in air, defying gravity. It does not go back, it floats in the air. If you keep on blowing, it floats in air. What is happening? When you are blowing over it, the pressure there gets reduced, and the high pressure from below lifts the ball, and ball floats in the air. So, these are two very interesting activities. You can find many more in books and on the internet if you search for these activities. We now take another important theorem or law called Torricelli's law. You see, the spellings are Torricelli. This person was an Italian, and therefore, the pronunciation is Torricelli law. And what is this law? This law states that the velocity of a flux of a fluid, what is the velocity of a flux? The velocity with which it comes out through a hole at depth h from the top surface is given by this. See what we have done here? We have taken a vessel. In this vessel, there is a fluid, water in this case, at constant height. You see, water comes here and flows out here. So, the height remains constant, and there is a small hole on this side. Because of the pressure of fluid, the fluid moves out of this, and this is the trajectory of the fluid, and the velocity with which it comes out, called velocity of a flux, is root of 2 g h. And you would recall, it is as if a body is fallen freely through a height h. It has gained velocity v after having fallen freely through height h. In this case, this is the velocity of a flux, the velocity with which the fluid comes out. So, very interesting phenomenon we see. Suppose again we take that vessel and we make 3 holes. The first is at depth h by 4, the second is at depth h by 2, the third is at depth 3 h by 4. We make 3 holes and let the water come out. You must have done this activity in your classroom in class 8 or 9 or maybe 10. I have taken this up because in most textbooks this figure is drawn wrongly. So, I am offering an explanation of Torricelli law. So, let us calculate what the distance covered by a stream coming out of say this hole or this hole or this hole. What is the horizontal distance that the fluid travels? Remember that we are considering the level of the bottom of this vessel at that level. Remember, this is at a depth of h by 4, this is at a depth of h by 4 plus h by 4, that is h by 2, this is at a depth h by 4 plus h by 4 plus h by 4, that is 3 h by 4. So, we have 3 holes. Let us label them 1, 2 and 3. 1 at a depth of h by 4, 2 at a depth of h by 2, 3 at a depth of 3 h by 4. Let us calculate now. The velocity of a flux from the first hole V 1 is 2 g into h by 4. H by 4 is the depth, you remember. Let me show you again. H by 4 is the depth, which is g h by 2. And when it comes out, this has to fall a distance 3 h by 4. This fluid has to fall, and we must find out the time that it takes for falling this, and then multiply by the velocity of a flux to find the horizontal distance by which it has travelled. That is the scheme. So, the time taken for this element of water just coming out to reach the ground level after covering a distance 3 h by 4 will be T 1, which will be equal to 2 g into 3 h by 4 square root. You recall your equations that distance covered is equal to half a t squared if the initial velocity is 0. So, from this we get 2 g into 3 h by 4. So, it is 3 g h by 2 square root of that. In this time, the horizontal distance covered by the stream will be what? Will be S 1, which would be equal to V 1 times T 1, V 1 times T 1, and you can multiply these two and you will see it is root of 3 by 2 into g h. Similar calculation we carry out for the other 2 holes, hole 2, hole 3. Similar, we get V 2 as root of g h, T 2 as the root of g h, S 2 is V 2 T 2, which is g h. S 1, S 2, S 3 are these distances, the horizontal distances. These are S 1, S 2, S 3. So, S 1 we have just calculated. Similarly, we can calculate S 2 and S 3, and we get S 2 is equal to g h, S 3 is equal to root 3 by 2 into g h. And you can now see that g h is the largest distance. This is root 3 is 1.73 divided by 2 is some 0.86 or something like that, and this is g h. So, that is why I have shown that the middle stream goes the highest distance horizontally, and the first and the third they travel horizontally the same distance. You can see that it is root 3 by 2 g h, root 3 by 2 g h. Clearly, the stream coming out of hole 2 travels farthest in the horizontal direction. Streams from hole 1 and 3 travel the same horizontal distance as we have shown above. I have gone to this length to explain to you this diagram, because many textbooks get it wrong. You see, the lowest stream is shown going through the largest distance, which as we have calculated is not true. if the vessel is placed at a certain height, say on a stool or even higher, then it is correct to show the lowest stream going the largest distance, because the pressure is highest. If you are talking of the level at which the vessel is placed, say vessel is placed on this tabletop, and you are considering here the where the streams strike, then the second one goes the highest distance. You would have realized that the situation is similar to that of a projectile, which has maximum range when it is projected at an angle of 45 degrees. In the next lecture, we have done with the fluid properties. In the next lecture, we shall start heat and thermodynamics, and we shall start with heat and temperature. We shall see what heat is, what temperature is, how temperature can be assigned to a substance, to an object, and how it is measured, and things like that. That is in the next lecture.
Dear students, in the chapter of photosynthesis, in the last session we discussed about light harvesting complex, that is LHC, and we know in this complex we have two main systems, the photosystem 1 PS1 and photosystem 2 the PS2, and also we discussed then photosystem 2 we have one reaction center which receives the light. From this point we move forward. We begin our discussion with electron transport. Let us understand how it is happening. We know then PS2, the photosystem 2, we have a reaction center which has capacity to receive the red light. The wavelength is such that it can receive the red light and will produce the electrons. They will move from PS2 to PS1, and we can also call it uphill. After that, it will come downhill and it will convert NADP into NADPH and H. Hence, electrons are produced. This is how the electrons are moving, which becomes very important for photosynthesis. Let us now understand this through the slide. We have electron acceptor, we have electron transport system, we have cytochromes, electron moving downhill and electron moving uphill, and this is all happening because of oxidation reduction reactions. Now, when all this is happening, which you can see in the slide, it is making a Z shape. Sometimes it is also called Z reaction or Z cycle. In the diagram, you can easily see how the light wavelength is trapped by reaction center, which is in photosystem 2, and how uphill task begins and they reach up to PS1, and then downhill task begins and NADP is converted into NADPH and H, and this is the electron system, the electron transport happening in our PS2 and PS1. The light harvesting system or the light harvesting complex plays the crucial role in making it possible. Children, you may be wondering why I should discuss splitting of water suddenly. What is the correlation? I of course told you about photosystem 2, photosystem 1 and the reaction center. We also know that reaction center has pigments and it receives light and produces electrons, and those electrons are moving from photosystem 2 to photosystem 1 and moves on for further reactions. that is the electron transport, we know it. Now the question is, how long the electrons will be produced in the reaction center? It may be exhausted at one point of time, then how this electron transport system will go on? The answer is splitting of water. Because of splitting of water, the electron is produced because the water, you know, H2O, it will split into hydrogen, oxygen and electrons. These are the electrons which are made available to PS2, the photosystem 2 continuously, and hence our electron transport system goes on. One more point which is coming out of splitting of water is, and which you should note, that the oxygen which is released from the plant during photosynthesis is coming from water, not from carbon dioxide. Plant takes carbon dioxide in photosynthesis and gives out oxygen, which is very important fact. But the oxygen which is released is not from CO2, carbon dioxide, but it is from H2O, the water. So, oxygen released, the gas for life, for our respiration, is coming due to splitting of water. So, you can understand how important the splitting of water is. It is not only providing oxygen to be released, it is also providing electrons so that the system of photosynthesis and other systems continue in the plant. We can also see this in our slide. You can see 2 H2O will give 4 hydrogen, oxygen and 4 electrons. And this system, the splitting of water system, is associated with PS2. Why PS2? Because PS2 has the reaction center and electrons are produced initially there. So, it should be associated at that point. And it is in thylakoid. You know the position of chlorophyll and the thylakoid, and helps in phosphorylation, that is conversion of ADP to ATP. ATP is the source of energy, and this is happening in mitochondria and of course in chloroplast. So, this is about splitting of water, and now we move forward. Chemoosmotic hypothesis, what it is about and how it works. We know that the final aim is to produce ATP and of course oxygen. Let us now discuss and study in this slide how this is taking place, and then I explain further. This is happening in thylakoid. So, thylakoid membrane is involved, proton pump is involved, proton gradient is involved, and of course enzyme ATPase is involved, which will convert ADP to ATP. Now, this membrane is important and many things are happening inside and outside the membrane. You can see photosystem 2 here. You can see photosystem 1 also in between cytochrome. You are also seeing the electrons H plus. Now, they are moving from photosystem 2 to photosystem 1, which you can see in this diagram, and finally ATP synthetase is helping ADP to be converted to ATP. Naturally, the electrons are used and they are produced again by splitting of water. Now, in this case, the proton pump is producing protons which are making proton gradient. This proton gradient is an important aspect. Only when this gradient breaks, then ATP is produced, and breaking will take place as the electrons are going on being produced, and then ADP is converted to ATP. So, this is chemoosmotic hypothesis, which explains majorly the proton pump and the proton gradient and breaking of gradient for the purpose for which we are doing all this discussion. We have understood about proton gradient of chemoosmotic hypothesis, that only when this gradient breaks, then the purpose is served, and this gradient will break due to movement of electrons across the membrane. Now, we will see that what is happening in dark reaction. We have already discussed light reaction in previous episodes. We know about ATP and NADPH. These are the products of light reaction. Please remember, the production of ATP and production of NADPH, these are product of light reaction. Now we move forward with this. It will result into synthesis of food, also release of oxygen, we know the details, and this is a biosynthetic pathway. Now this biosynthetic pathway we are calling dark reaction. Why? Because it is taking place in absence of light inside the thylakoid, inside the leaf. But it is not very correct to call it dark reaction, because it is taking place in the presence of product of light reaction. Please remember, ATP and NADPH are product of light reaction. That could not happen if light was not there. If sunlight was not available, ATP and NADPH could not be produced. And now this biosynthetic pathway or dark reaction could not take place if ATP and NADPH is not present. That means dark reaction is dependent on products of light reaction. Hence, we can say that light is equally responsible and important for dark reaction to take place. Students, we have discussed and understood many parts of photosynthesis. Now let us see what are the factors that affect photosynthesis. By now you know that photosynthesis is an important phenomenon and life cannot exist on earth without this process going on, and with that you also know the value of plants around us. You very well know we need sunlight for photosynthesis. So, first factor has to be light. We already know that another important factor for photosynthesis has to be carbon dioxide, and then comes water, because carbon dioxide and water in presence of sunlight will carry on photosynthesis and produce food plus oxygen. In addition to these three, temperature is another factor. Suppose the plant is in a frozen condition, or suppose it is boiling, then naturally photosynthesis will not take place. So, optimum temperature is also the need for photosynthesis. So, we can also include temperature in the factors which may affect photosynthesis. We will discuss about law of limiting factor and also factor at suboptimal level. Now, first let us start with the light. We know photosynthesis takes place during the day and it does not take place during the night because of absence of sun. That means light is important. In your class, in your laboratory, your teachers have helped you in understanding how in absence of light the leaf will not undergo photosynthesis. So, we can say that light is an important factor. If carbon dioxide is not made available experimentally to the leaf, then also photosynthesis will not occur, and that means carbon dioxide is also important, and we are very pleased to know this because we are producing lot of carbon dioxide and we want oxygen in exchange, and our plant friends are doing that for us. Water, which is again a basic need for plant and also for the photosynthesis. Now, when I talk of law of limiting factor, what do I mean by this? I mean that if photosynthesis is not taking place in a plant, then either one factor is important which is not working well, one factor may be responsible for this, or suppose 2-3 factors are responsible, 2-3 factors are affected at the same time, then law of limiting factor says that the photosynthesis will be affected by that factor which is at the minimal level. So, out of 2 or 3, the one which is at the minimal or subminimal level will eventually affect the photosynthesis. So, photosynthesis is definitely affected by so many factors, and if everything is okay, plant continues with photosynthesis, production of food and production of oxygen. At this point, I will remind you that this is photosynthesis where plants are taking carbon dioxide, giving out oxygen, but they are doing respiration also, in which they also take oxygen like us and they also give out carbon dioxide like us. In this session, we have discussed about electron transport system, splitting of water, oxygen coming out from water which is released by the plant. Also we have discussed chemoosmotic hypothesis and the dark reaction for which the product of light reactions are important, and then we also discussed the factors affecting photosynthesis like water, like carbon dioxide, like light, and law of limiting factor. With this we come to the end of this session. Thank you. Dear students, in this episode we plan to discuss Calvin cycle. First of all, we must know why it is important for us to know about Calvin cycle. In previous episodes, we have discussed about photosynthesis, different aspects of photosynthesis, and we know photosynthesis helps us in getting rid of carbon dioxide in the environment and getting oxygen from it. Is it the only purpose of photosynthesis? We had been telling about it, that by the process of photosynthesis, plants are able to make their food and release oxygen in the environment. So far, we have concentrated on understanding of how oxygen is produced in the process of photosynthesis. Now, it is equally important for us to know how food is synthesized in the plant by the process of photosynthesis, and that is a point where we need to understand Calvin cycle. Calvin cycle will explain that what are the steps which are taking place inside the plant tissue, so that carbon dioxide and water in the presence of sunlight are producing food in the form of starch or sucrose or glucose, which is being stored by the plant for their own use, and we also use the same food in form of using the fruits of the tree. We can understand details of Calvin cycle from the slide. First of all, it is a cyclical activity. Unless it was cyclical activity, the purpose could not be served. It has three major steps: carboxylation, reduction, and regeneration. And without all the three steps taking place, the cycle cannot be completed and cycle cannot be recycled. The cycle should continue, means it should be recycled again and again. It begins, for the sake of understanding, it begins with carboxylation. The ribulose 1,5-biphosphate, it will undergo carboxylation. Carboxylation is the main step in Calvin cycle. What happens in this step? It will make use of carbon dioxide, which is taken for photosynthesis, also water, and in the presence of enzyme, it will convert ribulose 1,5-biphosphate to 3-phosphoglycerate. This was carboxylation, use of carbon dioxide in Calvin cycle. Now, this 3-phosphoglycerate, at the cost of consumption of NADPH, which was product of light reaction, and also at the cost of ATP, which was also the product of light reaction, these two are utilized in the second step called reduction, where 3-phosphoglycerate is converted to glyceraldehyde 3-phosphate. I may repeat this step in a different way to make you understand better. Carboxylation has taken place and now reduction will take place. For that, we need to use, the plant needs to use NADPH and ATP, which was the product of light reaction, and using that it will convert 3-phosphoglycerate to glyceraldehyde and 3-phosphate, and in the process ATP is converted to ADP and of course phosphate molecule. Please remember, the plants are doing photosynthesis to get energy as ATP, to give out oxygen and also to make food. The energy such produced is not fully used for all the other processes in the plant. Part of ATP is also used to complete the process of photosynthesis to produce starch and glucose. So, whatever energy is produced, that is partly utilized by plant itself for this particular process. So, we have reached up to the point the formation of glyceraldehyde 3-phosphate after the process of reduction. Now, next step is very important. By series of steps, of course, starch is produced and sucrose is produced. This is a food for the plant. The plant will use it as a food and of course, we will also use. But now the next step called regeneration is more important than the previous step. Unless regeneration takes place, the cycle will not continue. Cycle will stop with the production of glucose and starch and full stop. How about the next? The next cycle has to continue so that food is continuously produced by the process of photosynthesis. So, in this regeneration, the plant will still use more ATP, which will be converted to ADP, and the end result will be ribulose 1,5 biphosphate, with which the Calvin cycle began. So, beginning is important, but replacement is also important. If cycle begins at this point, undergoes carboxylation, then reduction, then regeneration, then only it reaches to the first initial point again. Otherwise, cycle cannot continue. That is one thing to understand. Second thing to understand, what we are producing, the plant is producing in the form of ATP is partly utilized, plant is producing NADPH partly utilized, and that is converted to ADP. Normally, ADP is converted to ATP because we need energy, the plant needs energy, any living body needs energy. But here part of that ATP which was produced as energy is self utilized to complete this cycle in order to have food, the starch and the glucose. So, that is the purpose the Calvin cycle is serving in the plant's body, and this is called biosynthetic pathway because plant is producing biosynthetic material, that is glucose or sucrose or starch, which is stored in the plant for a long time and can be used by other organisms as well. I am sure this particular slide makes it very clear how this process is happening. Let me draw your attention on certain points. Now, you can see NADPH when used for Calvin cycle is converted to NADP like ATP to ADP. Adenosine triphosphate converted to adenosine diphosphate, that means plant has to give energy more to convert ADP to ATP. So, this is a complex process which will again run within the plant. Similarly, you can see 3 ATP consumed are giving out 3 ADP in the regeneration process. Of course, the plant had to shell out energy, but coming to the initial point of Calvin cycle is also important. So, cycle goes on. So, okay, this also happened. So, this is complex shuffling. This complex shuffling completes the cycle. In this, 15 carbons are produced at the initial point and 15 at the point where starch was synthesized, and the enzyme utilized was in carboxylation, Ribosco enzyme. So, enzyme utilization is only at the carboxylation, and of course, other processes are going on as explained in the cycle. With this, we complete Calvin cycle, which is biosynthetic pathway or biosynthetic cycle. It is named Calvin after the name of the person who described it in detail. We have discussed Calvin cycle and 3 important steps of Calvin cycle being carboxylation, reduction and regeneration. Now, I want to emphasize on the point using enzyme at carboxylation, where carbon dioxide is fixed, and that is Ribosco enzyme. Now, Ribosco is the enzyme which has affinity for oxygen as well as for carbon dioxide. In Calvin cycle, we have shown its affinity with carbon dioxide because it is being used in carboxylation and fixing carbon dioxide. And also I would like to remind you students that Calvin cycle takes place in C3 plants as well as C4 plants. But there is some difference between C3 and C4 plants that we will understand in the next slide. Difference between C3 and C4 plants is photorespiration. Photorespiration takes place only in C3 plants. What happens in this? As I told you while explaining Calvin cycle, that the enzyme ribosco at the level of carboxylation, it has equal affinity for oxygen and carbon dioxide, and when carbon dioxide is more, naturally it is working on carbon dioxide. But suppose oxygen is available, then if it is getting linked to oxygen, then photorespiration will begin. And what will happen? And that can begin only in C3 plants, not in C4 plants. So, there won't be any synthesis of ATP, no synthesis of NADPH, that means product of light reaction will not happen. There is no synthesis of sugars, that means food is not prepared by the plant nor stored. And instead of oxygen, carbon dioxide is released utilizing ATP. So, whatever ATP is present in the plant, that is also being used to produce carbon dioxide, which we do not require, we require oxygen. So, this is considered a wasteful process. It can take place in C3 under certain circumstances, but whenever it is taking place, it is a wasteful process and it does not take place in C4 plants. And that is why C4 plants are considered more stable. They can survive in slightly higher temperatures or variable temperatures and carry on photosynthesis well and also Calvin cycle well, so that they are though using ATP, but also producing oxygen and also continuing with the Calvin cycle to produce sugar and starch as their food material. Now, in C3 plants, as I am discussing the photorespiration, when will it take place and how it will take place? Only when the proportion between availability of oxygen and availability of carbon dioxide is such that ribosco enzyme at the level of carboxylation gets attached to oxygen in place of carbon dioxide. And the moment that happens, carboxylation will not take place. That means, I am going to the previous slide to make you understand this. Carboxylation, the ribosco enzyme, carbon dioxide is being used in this process of Calvin cycle. Suppose carbon dioxide was not used, suppose it was photorespiration, then in place of CO2 there will be O2. Hence, carboxylation cannot take place. Now, the total cycle will change, all the steps will change, and instead of producing food, it will not produce food. Instead of producing oxygen, it will produce carbon dioxide and it will consume ATP to produce carbon dioxide. That means, neither carboxylation will take place nor reduction will take place, and regeneration will also not take place, and Calvin cycle will not be able to serve the purpose for what it is taking place inside the plant. So, photorespiration, which is a wasteful process, sometimes takes place in the situation where the proportion between oxygen and carbon dioxide is such that this particular enzyme, the important enzyme, the most abundant enzyme in the plant kingdom, the ribosco, gets fixed with oxygen in place of carbon dioxide. So, students, we have discussed about Calvin cycle, its utility and also photorespiration, and we have discussed the conditions in which these particular cycles take place. We have understood the utility of Calvin cycle in the plant. Children, it is time for you to appreciate the efforts made by plants for us and how complicated the system is and how complicated the reactions taking place within the plant body to give us oxygen and of course food in addition to many other things which we get from the plant. Also try to imagine if any step is disturbed by any of the factors or man-made factors or natural factors, that means this cyclical activity will be affected, and unless cycle is completed, neither we can get oxygen properly, nor we can get food properly, nor plant can get ATP. Also, one more point which is made clear from this discussion, that whatever energy is produced by plant, at least half of it is utilized in making Calvin cycle possible. With this, we come to the end of this session. Thank you. Students, today we are discussing respiration in plants. When the word respiration comes, obviously we feel taking in oxygen and giving out carbon dioxide. Of course, that is the process, but we will try to understand why it is happening and why plants and all the animals need to do it. Respiration is a common occurrence, a common physiological process in all the living beings, including all the animals and all the plants, with the exception of some which are anaerobes. When it comes to respiration in plants, we have also heard and discussed sometimes or the other the process of photosynthesis, which is when plants take carbon dioxide and give out oxygen. In respiration, plants take oxygen and give out carbon dioxide exactly the way we do it. In respiration, there is one process called breathing. Breathing is simple exchange of gases, taking in oxygen, giving out carbon dioxide. Now, we have to understand why it is happening, why we need to take oxygen, why plants need to take oxygen. Is that the purpose of respiration? Are we respiring or plants are respiring for the purpose of getting oxygen? Perhaps answer is more complicated than the question. The question seems to be very simple. The answer is that breathing is going on to take oxygen, but not for the sake of taking oxygen. It is happening to produce energy. Energy is produced by oxidation of macromolecules, and for that oxidation we require oxygen. So, oxygen is eventually required for breaking down of macromolecules for the production of energy. This is what we are going to understand in this particular session. So, energy need is important for every living organism, plant or the animal. Now, that energy has to come from somewhere. We eat food and we get energy, but that food is to be burnt in the presence of oxygen which we breathe in. Now, plants, they are not eating food, they are rather synthesizing food. Even if they are synthesizing food through photosynthesis, that food will not give energy directly. It will give only when it is burnt or broken down to simpler substances in the presence of oxygen, in other words, when it is oxidized. For that, plant needs oxygen. So, process of breathing eventually leads to production of energy or release of energy. Students, you know, photosynthesis takes place in leaves because leaves have the machinery for photosynthesis. Respiration takes place in almost all the cells which are in connection with the environment. We now discuss about energy. Energy is important for plant and oxidation of macromolecule is taking place. That means breaking down of CC bonds for the production of energy in the form of ATP is the respiration. Green plants do photosynthesis in the presence of sunlight using carbon dioxide and water, and in turn give out energy and oxygen. Now, during daytime, this oxygen is easily available to plant within the leaf. It is produced within the leaf because photosynthesis is taking place within the leaf. So, availability of oxygen is not a problem when sun is there or when daylight is there or when photosynthesis is taking place. Green plants and cyanobacteria, these two categories have chlorophyll, chloroplast, hence they can produce or synthesize their own food in the presence of sunlight with the help of chlorophyll. That means these two categories are autotrophs. Auto, self, trophs, food, producing food themselves. So, green plants and cyanobacteria are able to synthesize their food themselves, whereas all other organisms depend on plants for their food directly or indirectly. As we have discussed, food, the source of food in cyanobacteria and in green plants is photosynthesis. Children, you can very well appreciate at this point the value of photosynthesis and value of plants for our livelihood. In this case, that means in case of photosynthesis, the light energy is converted to chemical energy. How? Light energy is sunlight. With the help of water and carbon dioxide, it is converted to ATP or the energy which is chemical form of energy. Now, this energy is stored in plant in the form of glucose, sucrose, starch, and is acted upon by oxygen of breathing to be converted to ATP. Children, please try to understand one point separately, and that is the food which is formed by photosynthesis is not giving energy to the plant. Only when oxygen acts on it, it is converted to chemical form of energy, that also not in one go, in small steps, step by step, so that energy is stored in the form of ATP, which is chemical energy, and it remains stored there till it is required by plant to be utilized. Even in your case, the energy is stored in the form of ATP and is used if and when required by your body. If storage was not possible, in that case the moment we eat food, energy is consumed. Energy is given to body and body consumes it. The moment photosynthesis is done, energy comes to plant and it is exhausted. That should not happen, and that is why the energy is converted to chemical form of energy, which is called ATP, adenosine triphosphate, and remains there and is released if and when required. You can see in the slide the photosynthesis. This is leaf having chlorophyll. This is sunlight is coming from sun, of course. Water is absorbed by roots and reaching the leaf. Then carbon dioxide which we are giving out, and end result is oxygen and the starch. Oxygen comes to atmosphere which we require for our respiration, and starch is stored in the plant to be converted to ATP in the presence of oxygen. We are now discussing a few points regarding photosynthesis. We know it takes place in green trees, green plants, in the leaves, mainly in the leaves, because leaves have chloroplast, and inside the chloroplast there is a green pigment called chlorophyll, and this chlorophyll does the trapping of sunlight. Trapping of sunlight is important because unless sunlight is trapped, photosynthesis cannot occur. At this point, we should also appreciate that sun is the eventual source of energy on earth. Of course, it is trapped by the trees, and that is why trees are also important. In the green parts of the plant, the food is synthesized, but in the tree or in the plant, there are some non-green parts also. So, this food is translocated to different parts of the plant, and plant has machinery for this. Plants or trees, they are autotrophic, they are synthesizing their own food, whereas all the animals are either heterotrophic or they fall in some other categories which we are going to discuss. If heterotrophic, then again there are two categories, herbivores and carnivores. Herbivores which depend on plant food, and carnivores which are eating herbivores. But whatever the case may be, whether animal is herbivore or carnivore, eventually it is depending on the plant, because herbivore is eating plant and carnivore is eating herbivore which has eaten plant. So, if you see food chain, even carnivore is dependent on the plants. Then there are fungi which feed on dead organic matter, and they are called saprophytes. Coming back to respiration, we were trying to understand a part of photosynthesis, chloroplast, etc., to understand respiration in a nice way. We have understood that eventual source of energy is photosynthesis. Now, cellular respiration takes place in the cell. The result is breakdown of food material. Let me elaborate this point. In photosynthesis, the food was synthesized within the leaf. It was in the leaf cell. Now, inside the cell, food is there, but it will not give energy unless oxygen is available through breathing or respiration. That oxygen will break this food in the leaf, and out comes the ATP, that is a form of energy. So, it happened because breaking of macromolecule took place, and the result was production of energy which was produced in the form of heat also. So, synthesis of ATP is the final aim of respiration. Photosynthesis takes place in chloroplast, which we have already discussed, and breakdown of complex molecules takes place inside the cell cytoplasm to yield energy which is happening in cytoplasm and in the mitochondria. So, children, please try to understand that photosynthesis took place in chloroplast, the food was stored in the cell, and breaking down of macromolecule in the presence of oxygen took place in the cytoplasm, and that also in a organelle called mitochondria. And that is why mitochondria is called powerhouse of the cell, because energy is finally produced at this point. Release of energy in this fashion is in fact respiration. I am sure, children, you have now understood that why respiration is taking place and what is its aim. The aim of respiration is not make available oxygen to you only or to the plant. The aim of respiration is to make oxygen available for the production of energy, for the production of ATP. Only when ATP is produced, the aim of respiration is fulfilled. But respiratory substrate has to be there. What do I mean by substrate? Substrate is the base on which action takes place. In this context of respiration, respiratory substrate will be the food on which oxygen is acting to produce energy. So, respiratory substrate should be present so that energy can be produced. So, the respiratory substrates. Usually carbohydrates are the respiratory substrate because C-C bond is to be broken by oxygen. So, normally in plants carbohydrates act as respiratory substrate for the production of energy, but sometimes under certain circumstances proteins, fats and organic acids can also be used as respiratory substrates. Energy released in series of slow steps. What do I mean by this? Some substrate is acted upon by oxygen, some energy is produced. Again some more substrate is acted upon by oxygen, some more energy is produced. That means energy is not produced in one go. That is important. It should not be produced in one go, and it cannot be. Otherwise, a living body cannot remain living. And it is after that also stored as ATP, the chemical form of energy. Again, ATP remains stored and is utilized only when required, and that is the reason why we call ATP as energy currency of the cell. Currency means you have currency in your pocket, you will take out and use whenever you require. You earn, you get the salary in one go, but you use it during the time, many days, many weeks or the month. So, currency means it remains in the cell and is utilized whenever body requires it, and again that is also important step. So, 2 points to understand here will be that neither energy is produced in one go nor used in one go. It is produced stepwise and it is used as per the requirement of the plant body in this context. ATP, adenosine triphosphate. Energy produced to be converted to ATP, we have understood. ATP is energy currency of cell, that also we have discussed. Various energy requirement processes in the body like playing sports in case of human beings or running, hunting in case of animals, and other processes in the plants like growth or production of new leaves or formation of flowers or fruits. All these processes require energy, and this energy is utilized bit by bit as per the requirement. So, eventual energy used and stored is ATP. Plants breathe. How they breathe? Of course, breathing involves taking in oxygen and giving out carbon dioxide. Now, in the leaves, there are small pores, we call them stomata. You can see stomata in this slide, but they are present only in leaves. Do you mean to say that only leaves are doing the respiration? Children, at this point we must understand that plants or the trees, they do not have elaborate respiratory system like you have. You have your nose, you have trachea, lungs, alveoli and so many fine structures for respiration. In the plants, the respiratory part is very simplified. Stomata are present on leaves and they have guard cells which help in closing or opening of stomata, and exchange of oxygen and carbon dioxide takes place through these stomata. But stomata are present only on leaves. In other parts of the plant, say twigs or stem or near the bark, main stem of the tree, we have lenticels which are also small pores and help in exchange of gases. So, in case of plant, the whole body of the plant is involved in respiration because all the living cells in plant normally are exposed to the external environment. You may ask that stem is so thick, how it is exposed to air? The interior part of stem is made up of dead cells for the mechanical support. The outer layer just below the bark, that is made up of living cell and that is in connection with the air or the outside environment. So, each cell of the tree is respiring and fulfilling its own needs. So, children, in this particular episode, we have discussed about breathing, respiration, photosynthesis, chloroplast, chlorophyll, and the purpose of respiration, not only taking in oxygen, but production of energy in the form of ATP and conversion of light energy into chemical energy and also we discussed stepwise formation of this energy and release of energy slowly as per the requirement of plant. With this, we come to the end of this session. Thank you.
मिस्र अफ्रीका के उत्तर पूर्वी भाग में स्थित है। इसकी सभ्यता सबसे पुरानी मानी जाती है। यह देश पश्चिम और पूर्व में मरुस्थल से घिरा हुआ है, इसलिए सूखा और रेतीला है। यहाँ की भूमि को नील नदी का उपहार मिला है। नील नदी सारे मिस्र में बहती हुई भूमध्य सागर में मिलती है। नील नदी की घाटी मिस्र का सबसे उपजाऊ भाग है। मिस्र सभ्यता का विकास इसके किनारों पर हुआ। उस समय वहाँ राजा का शासन चलता था। वहाँ की भाषा हिब्रू में राजा को फ़ैरो कहा जाता था, जिसे रा नाम के देवता का पुत्र माना जाता था। रा यानी सूर्य देवता। सूर्य को वहाँ सबसे महत्वपूर्ण देवता के रूप में माना जाता था। देश के शासन कार्यों में कुलीन परिवारों के अलावा पुजारी, कर्मचारी, कलाकार, हस्तशिल्पी और किसानों की विशेष भूमिका होती थी। मिस्र की महिलाएं राजा की उत्तराधिकारी हो सकती थी। वहाँ के लोगों का विश्वास था कि मृत्यु के बाद भी मनुष्य में जीवन रहता है, इसलिए वे मृत शरीर को कुछ विशेष तरीकों से संरक्षित करते थे, जिसे ममी कहा जाता है। फिर इसे ताबूत में सजाकर पिरामिड्स में रखा जाता था। आज भी ये पिरामिड सैलानियों के आकर्षण का केंद्र है। ये पिरामिड कायरो के निकट गीज़ा में है। गीज़ा में स्फिंक्स मूर्ति कला का एक उत्तम उदाहरण है। स्फिंक्स एक पौराणिक जानवर है, जिसका सिर मनुष्य का और शेष भाग सिंह का है। सन 1920 के दशक में तूतनखानम मकबरे में कई वस्तुएं जैसे सिंहासन, गहने, संदूक आदि भी मिले, जो उन्होंने मृत व्यक्तियों के इस्तेमाल के लिए रखे थे। एक बहुत ही खूबसूरत कप मिला। कैरो में मिस्र की पुरानी चीज़ों का म्यूज़ियम बनाया गया। मिस्र वासियों ने मंदिर भी बनाए। कानार्क और अबू सिम्बल के मंदिरों में देवताओं, राजाओं और आम आदमी के रोज़मर्रा के जीवन को दर्शाते हुए विभिन्न दृश्यों की झांकियां हैं। यहाँ की लिपि चित्रों पर आधारित है, जिसे हायरोग्लाइफिक कहते हैं। ऐसा माना जाता है कि उस समय इस लिपि में लगभग 600 चिन्ह थे। युग बदला, फिर वहाँ पर्शियन, ग्रीक, रोम, अरब और तुर्क लोग आए। उनका राज्य स्थापित हुआ। यहाँ के बाज़ारों में आज भी इन सब देशों की संस्कृति की छाप लिए कलाकृतियाँ, शैंडलियर्स, लैम्प्स और सजावट का बहुत सा सामान दिखाई देता है। यह सब सैलानी को बहुत लुभाता है। यहाँ नए शहरों का निर्माण हुआ। अलेक्जेंडर पोर्ट शिक्षा का केंद्र बना। 1960 में मिस्र वासियों ने एक नया बांध असवान बनाया। आज भी सैकड़ों सैलानी मिस्र की प्राचीन सभ्यता को देखने के लिए आते हैं।
आज हम आपका परिचय करवाते हैं एक विशेष प्रकार की त्रिविमीय ठोस आकृति से, जिसने मानव जीवन की विकास और सभ्यता की कहानी में एक विशेष स्थान पाया है। लगभग 2000 और 3000 ईसा पूर्व मिस्र के सभ्यता के वैभव का अभिन्न अंग ये भव्य इमारतें उनके एक अनूठी कहानी कहती हैं। इन्हें कौन नहीं पहचानता, आप भी पहचानते हैं। ये है विश्व के 7 आश्चर्यों में से एक, मिस्र के प्रसिद्ध पिरामिड। मंदिर में बजती हुई घंटियों ने आपका ध्यान अपनी ओर आकर्षित किया होगा। क्या कभी आपका ध्यान मंदिर की चोटी की तरफ गया? उसके आकार की तरफ ध्यान दें। इन सभी विशेष प्रकार के ठोस आकृतियों को हम उनके प्रारूप द्वारा समझते हैं। इस ठोस आकृति को देखिए, इसका आधार षट्भुज के आकार का है और इसके पार्श्वीय फलक त्रिभुजाकार आकार के हैं। त्रिभुज आकार के इसके पार्श्वीय फलक हैं सभी, और ये सभी पार्श्वीय फलक एक उभयनिष्ठ बिंदु से आपस में जुड़े हुए हैं। इस ठोस आकृति में इसका आधार पंचभुज है, 5 भुजाएं हैं इसकी, और इसके पार्श्वीय फलक भी त्रिभुजाकार हैं, और ये सभी त्रिभुजाकार पार्श्वीय फलक ऊपर जाकर के एक शीर्ष बिंदु से, उभयनिष्ठ शीर्ष बिंदु से जुड़े हुए हैं। यह एक अन्य ठोस आकृति है। इस आकृति के आधार को देखें तो इसका आधार वर्ग के आकार का है और इसके भी पार्श्वीय पृष्ठ त्रिभुजाकार आकार के हैं। त्रिभुज, यह भी त्रिभुज और यह भी त्रिभुज, और ये सभी पार्श्वीय पृष्ठ आपस में एक शीर्ष बिंदु से जुड़े हुए हैं। यह एक और अन्य इसी प्रकार की ठोस आकृति है। इसका आधार त्रिभुज के आकार का है और इसके पार्श्वीय फलक त्रिभुजाकार हैं। ये भी त्रिभुज है और यह पार्श्वीय फलक भी त्रिभुज के आकार का है, और ये तीनों पार्श्वीय फलक एक शीर्ष बिंदु से आपस में जुड़े हुए हैं। तो इन सभी ठोस आकृतियों में हम क्या समानताएं पाते हैं कि इन सभी ठोस आकृतियों के आधार बहुभुज हैं और पार्श्वीय फलक त्रिभुज हैं, और ये सभी एक उभयनिष्ठ शीर्ष बिंदु से जुड़े हुए हैं। तो इस प्रकार की आकृतियों को हम कहते हैं पिरामिड। तो पिरामिड कैसी आकृतियां हुई? पिरामिड समतल पृष्ठों से बनी ठोस आकृति है जिसका आधार बहुभुज होता है तथा शेष पृष्ठ त्रिभुज होते हैं। इन त्रिभुजाकार पृष्ठों का एक उभयनिष्ठ शीर्ष आधार तल के बाहर होता है। अब इन पिरामिड के आधार जिस आकार के होते हैं उसी नाम से हम उन्हें पुकारते हैं। यह एक उसी प्रकार की ठोस आकृति है। इसके 4 त्रिभुजाकार फलक हैं, एक आधार त्रिभुज के आधार का और 3 त्रिभुजाकार पार्श्वीय फलक। तो कुल इसके 4 फलक हैं, तो इसे हम चतुष्फलक भी कहते हैं। आज हम त्रिभुजीय पिरामिड या चतुष्फलक जिसे हम कह रहे हैं उसके बारे में और अधिक जानकारी हासिल करें। यह एक पिरामिड है त्रिभुज आधार का। इस पिरामिड के आधार का ये केंद्रक हमने मार्क किया हुआ है। अब अगर आधार के केंद्रक को हम शीर्ष से जोड़ें तो यह जो रेखाखंड है आधार के केंद्रक को शीर्ष से मिला रहा है, यह है अगर आधार पर लंब हो तो पिरामिड जो है लंब पिरामिड कहलाता है। यह लंब त्रिभुजीय पिरामिड है। इसके पार्श्वीय फलक 3 हैं और ये जो किनारे हैं इन्हें हम पार्श्वीय कोर कहते हैं। इसकी पार्श्वीय कोर कितनी है? 1, 2 और 3 पार्श्वीय कोरें हैं और 3 और भी कोरें हैं आधार की, 1, 2 और 3, अर्थात इसकी कुल 6 कोरें हुई। 3 पार्श्वीय कोरें और कुल 6 कोरें। और इसके शीर्ष कितने हैं? एक यह शीर्ष है, एक यह शीर्ष है, एक यह शीर्ष है और एक यह शीर्ष। इसके 4 शीर्ष हैं। इसके आधार के मध्य बिंदु को शीर्ष से मिलाने वाला रेखाखंड पिरामिड की तिरछी ऊंचाई कहलाती है। और अधिक जानने के लिए हम पिरामिड के पार्श्वीय फलकों को खोलते हैं। अब देखिए, ये पार्श्वीय फलक त्रिभुजाकार के हैं और अगर हम इन पार्श्वीय फलकों को इस प्रकार खोल करके रख लें और इन पार्श्वीय फलकों को एक दूसरे के ऊपर रख करके देखें तो हम पाते हैं कि ये तीनों ही पार्श्वीय फलक क्या है, सर्वांग समत्रिभुज हैं। देखिए, तीनों पार्श्वीय फलकों ने एक दूसरे को पूरी तरह से ढक लिया और इनकी यह भुजा क्या है, पार्श्वीय कोण। तो क्या मतलब हुआ कि ये जो पार्श्वीय कोणें हैं ये क्या हैं, आपस में समान हैं। और इसके बारे में एक और जानकारी आपको हम देते हैं कि यह इस भुजा का मध्य बिंदु है और इसको हमने इस शीर्ष से मिलाया है, तो यह इसका इस त्रिभुज का लंब समद्विभाजक भी है, क्योंकि इसकी ये भुजाएं आपस में क्या है, बराबर हैं। तो यह जो लंबाई है यह पिरामिड की तिरछी लंबाई भी, तिरछी ऊंचाई भी कहलाती है। अब अगर आप चाहें कि हम एक इस प्रकार का पिरामिड बनाएं, तो सबसे पहले तो आपको यह जानना होगा कि इस पिरामिड को बनाने के लिए आपको कितना कार्डबोर्ड या चार्ट, जिस भी वस्तु से आप इसे बना रहे हैं, वो कितनी चाहिए। और वो जानकारी हासिल करने के लिए आप क्या करेंगे, आपको इस पिरामिड का संपूर्ण पृष्ठ क्षेत्रफल ज्ञात करना होगा। संपूर्ण पृष्ठीय क्षेत्रफल अर्थात इसके ये तीन पार्श्वीय फलक हैं, पार्श्व पृष्ठ का क्षेत्रफल और इसके आधार का क्षेत्रफल, यह आपको ज्ञात करना होगा। तो सबसे पहले हम सीखते हैं कि इसके आधार का क्षेत्रफल हम किस प्रकार से ज्ञात करेंगे और उसके लिए हम इस पिरामिड को खोलेंगे। खोलने पर हमने पाया कि पिरामिड में ये तीन पार्श्वीय फलक जो हैं वो त्रिभुज के आकार के हैं और एक आधार है त्रिभुज के आकार का। तो पार्श्व पृष्ठ क्षेत्रफल निकालने के लिए हम इस त्रिभुजों का क्षेत्रफल निकालेंगे, क्योंकि ये तीनों त्रिभुज ही सर्वांगसम हैं। तो इसके लिए हम एक त्रिभुज का क्षेत्रफल पहले निकालेंगे। त्रिभुज के मध्य बिंदु को हम सम्मुख शीर्ष से मिलाते हैं और जैसा कि आप जानते हैं कि यह है तिरछी ऊंचाई और तिरछी ऊंचाई को हम नाम दे देते हैं L का। और ये है आधार, आधार जो कि समबाहु त्रिभुज के आकार का है, इसकी भुजा को हम नाम दे देते हैं A। अब अगर त्रिभुज में आपको लंब पता हो और आधार का माप पता हो तो त्रिभुज का क्षेत्रफल क्या होता है, 1/2 गुणा आधार गुणा लंब। तो इसका क्षेत्रफल क्या होगा, 1/2 गुणा A गुणा L। इसी प्रकार क्योंकि यह त्रिभुज इस त्रिभुज के सर्वांग सम है, तो इसका क्षेत्रफल भी होगा 1/2 गुणा A गुणा L। और इसी प्रकार इस त्रिभुज का क्षेत्रफल भी होगा 1/2 गुणा A गुणा L। और तीनों के क्षेत्रफल को अगर हम मिला लें तो तीनों का क्षेत्रफल जो है वो क्या हो जाएगा, 3/2 A गुणा L। तो इसका पृष्ठीय क्षेत्रफल क्या हुआ, 3/2 गुणा A गुणा L। और अभी इसमें हमने आधार का क्षेत्रफल शामिल नहीं किया है। आधार कैसा है, यह समबाहु त्रिभुज के आकार का है। इसकी भुजा की माप अगर हम मान लें कि A है तो इसका क्षेत्रफल क्या होगा, वर्गमूल 3/4 A की घात 2। तो हमने ज्ञात किया कि पार्श्व पृष्ठ क्षेत्रफल क्या होता है, 3/2 गुणा A गुणा L, या हम ये भी कह सकते हैं कि 1/2 गुणा आधार का परिमाप गुणा तिर्यक ऊंचाई। संपूर्ण पृष्ठ क्षेत्रफल होता है पार्श्व पृष्ठ क्षेत्रफल जमा आधार का क्षेत्रफल, यानी कि यह होता है 3/2 AL, जहाँ पर A है आधार की भुजा, L है तिर्यक ऊंचाई, जमा वर्गमूल 3/4 A की घात 2। तो ये हमने सीखा कि किस प्रकार हम पार्श्व पृष्ठ क्षेत्रफल और संपूर्ण पृष्ठ क्षेत्रफल निकालते हैं। तो क्यों ना हम कुछ इससे संबंधित प्रश्नों को हल करके देखें। किसी लंब पिरामिड का आधार समबाहु त्रिभुज है जिसकी प्रत्येक भुजा 4 मीटर लंबी और इसकी प्रत्येक तिरछी कोर 3 मीटर लंबी है। पिरामिड का पार्श्व पृष्ठ का क्षेत्रफल ज्ञात कीजिए। अब इस प्रश्न में हमें समबाहु त्रिभुज के आधार की भुजा की लंबाई दी है और तिरछी कोर दी है। इस प्रश्न को हल करने के लिए हम पिरामिड के मॉडल का प्रयोग करते हैं। यह पिरामिड का मॉडल है और इसको हल करने के लिए हम इसके नामांकन करते हैं। शीर्ष का नाम हम रखते हैं ओ, ए और बी। हमें चाहिए क्या? हमें चाहिए इसके तिरछी ऊंचाई, और उसके लिए हम क्या करते हैं कि हमें दिया क्या हुआ है, इसकी पार्श्वीय कोर कितनी लंबाई है? पार्श्वीय कोर की लंबाई है 3 मीटर और आधार की लंबाई हमें कितनी दी है? इस भुजा की लंबाई हमें दी है 4 मीटर। ऐसा हम क्यों कर रहे हैं? क्योंकि हमें पिरामिड की तिरछी ऊंचाई ज्ञात करनी है। पार्श्व पृष्ठ क्षेत्रफल ज्ञात करने के लिए हमें पिरामिड की तिरछी ऊंचाई का पता होना जरूरी है। अब देखिए, ODB एक समकोण त्रिभुज है और हम जानते हैं पाइथागोरस प्रमेय द्वारा कि समकोण त्रिभुज में कर्ण का वर्ग शेष दो भुजाओं के वर्गों के योग के बराबर होता है। तो त्रिभुज ODB में OB का वर्ग बराबर होगा OD का वर्ग जमा BD का वर्ग। तो हम कह सकते हैं कि यहाँ पर OD का वर्ग जो हमें ज्ञात करना है वो किसके बराबर होगा? OB का वर्ग घटा BD का वर्ग, और OD की लंबाई जो है वो बराबर होगी OB का वर्ग घटा BD का वर्ग और इसका वर्गमूल। और इसका माप हमें दी है, OB की लंबाई कितनी दी है? 3 का वर्ग माइनस BD क्या है? भुजा का आधा यानी 4 का आधा, तो ये हो गया 2 का वर्ग और इसका वर्गमूल इतना मीटर। तो इसकी पैमाइश किसके बराबर होगी? वर्गमूल 5 मीटर। अब ये तो हमने निकाली उसकी तिरछी ऊंचाई और हमें निकालना क्या है? उसका पार्श्व पृष्ठ क्षेत्रफल। तो पार्श्व पृष्ठ क्षेत्रफल क्या होता है? 1/2 गुणा आधार का परिमाप गुणा तिर्यक ऊंचाई। तो ये किसके बराबर होगा? 1/2 गुणा 3 गुणा 4 गुणा वर्गमूल 5 और इसके साथ क्या आएगा? वर्ग मीटर। और इसको हल करने पर आएगा 6 वर्गमूल 5 वर्ग मीटर। और चाहे तो इसको आप आगे और हल कर सकते हैं, वर्गमूल 5 का मान निकाल करके, तो इसका मान आएगा 13.44 वर्ग मीटर। तो आइए एक और प्रश्न हल करें जिसमें हमें इससे कुछ विभिन्न जानकारी दी हो। एक लंब पिरामिड का आधार समबाहु त्रिभुज है जिसका क्षेत्रफल 16 वर्गमूल 3 वर्ग सेंटीमीटर है और तिरछी ऊंचाई 3 सेंटीमीटर है। पिरामिड का पार्श्व पृष्ठ और संपूर्ण पृष्ठ क्षेत्रफल ज्ञात कीजिए। अब इस प्रश्न में हमें क्या जानकारी दी गई है? हमें आधार का क्षेत्रफल बताया गया है 16 वर्गमूल 3 वर्ग सेंटीमीटर और तिरछी ऊंचाई दी है 3 सेंटीमीटर। ज्ञात क्या करना है? पिरामिड का पार्श्व पृष्ठ और संपूर्ण पृष्ठ क्षेत्रफल। उसके लिए हमें क्या पता होना चाहिए? आधार की भुजा का माप, और हमें दिया क्या है? आधार का क्षेत्रफल। आधार समबाहु त्रिभुज है और समबाहु त्रिभुज का भुजा का माप अगर a हो तो क्षेत्रफल क्या होता है? वर्गमूल 3/4 a की घात 2 और उसकी माप हमें किसके बराबर दी है? 16 वर्गमूल 3 वर्ग सेंटीमीटर। तो यहाँ से a की घात 2 का मान आया 64 और a का मान हुआ 8 सेंटीमीटर। तो ये हमने ज्ञात की पिरामिड के आधार की भुजा। और अब हमें ज्ञात करना है उसका पार्श्व पृष्ठ क्षेत्रफल और संपूर्ण पृष्ठ क्षेत्रफल। तो उसका पार्श्व पृष्ठ क्षेत्रफल क्या होता है? 1/2 गुणा 3a गुणा l, जहाँ पर a क्या है? आधार की भुजा, l क्या है? तिरछी ऊंचाई। तो ये किसके बराबर हुआ? 1/2 गुणा 3 गुणा 8 गुणा 3, ये हुआ 36 वर्ग सेंटीमीटर। अब और क्या हमें इसमें निकालना है? संपूर्ण पृष्ठ क्षेत्रफल। तो अब हम संपूर्ण पृष्ठ क्षेत्रफल निकालेंगे। वह क्या होता है? पार्श्व पृष्ठ क्षेत्रफल में अगर हम आधार का क्षेत्रफल जोड़ दें तो वो क्या होगा? संपूर्ण पृष्ठ क्षेत्रफल। अब पार्श्व पृष्ठ क्षेत्रफल हमने निकाला, कितना है? 36 वर्ग सेंटीमीटर। आधार का क्षेत्रफल हमें प्रश्न में ही बताया गया है, वह कितना है? 16 वर्गमूल 3। तो इन दोनों को हमने जोड़ दिया, 36 + 16 वर्गमूल 3 वर्ग सेंटीमीटर क्या होगा? इसके संपूर्ण पृष्ठ का क्षेत्रफल। तो अब आप इस प्रकार के और प्रश्न जो है स्वयं हल करके देख सकते हैं। अब अगर हमें एक पिरामिड, त्रिभुजीय पिरामिड बनाना हो धातु का, तो सबसे पहले हमारे दिमाग में प्रश्न आएगा कि उसको बनाने के लिए कितनी धातु प्रयोग होगी, और कितनी धातु प्रयोग होगी यह जानने के लिए हमें क्या करना होगा? पिरामिड का आयतन ज्ञात करना होगा। अब पिरामिड का आयतन हम किस प्रकार ज्ञात करेंगे? उसके आयतन को ज्ञात करने के लिए हम प्रिज्म का सहायता लेंगे, और प्रिज्म का आयतन तो आपको पता ही है क्या होता है। तो हम एक जैसी ऊंचाई के और एक जैसे आधार वाले एक पिरामिड और एक प्रिज्म लेते हैं, और हम प्रिज्म में द्रव डालेंगे पिरामिड में भर के। जितना उसमें द्रव आएगा उसको हम क्या कहेंगे कि वो आयतन का उनका हमारे पास संबंध आ जाएगा। तो इस क्रिया को हम करते हैं। ये हमने इसमें ऊपर तक पानी भर के लिया और इसे हम प्रिज्म में उड़ेलते हैं। ये हमने देखा कि एक बार इस प्रकार भरकर डालने पर यह नहीं भरा, तो हम दोबारा से उसे करते हैं। पानी लेंगे पिरामिड में और प्रिज्म में डालते हैं, अभी भी ये नहीं भरा, तो एक बार फिर पानी लेते हैं, और इस प्रकार हम पाते हैं कि 3 बार हमने पिरामिड में पानी भर के प्रिज्म के अंदर डाला और यह प्रिज्म जो है बिल्कुल ऊपर तक भर गया। इसका मतलब क्या है कि पिरामिड का आयतन क्या है? प्रिज्म के आयतन का 1/3। और प्रिज्म का आयतन क्या होता है? यह तो आप जानते ही हैं, आधार का क्षेत्रफल गुणा इसकी ऊंचाई। तो पिरामिड का आयतन क्या होगा? 1/3 गुणा आधार का क्षेत्रफल गुणा ऊंचाई। और अगर हम आधार की भुजा को मान लें a और उसकी ऊंचाई को मान लें h, तो ये किसके बराबर होगा? वर्गमूल 3/12 a की घात 2 h। अब क्यों ना हम कुछ आयतन संबंधी प्रश्नों को हल करके देखें। एक लंब पिरामिड का आयतन ज्ञात कीजिए जिसकी ऊंचाई 4 मीटर और जिसका आधार 1 मीटर भुजा का समबाहु त्रिभुज है। अब इस प्रश्न में हमें क्या दिया है? इस प्रश्न में हमें ऊंचाई दी है जिसको हम मान लेते हैं h, कितना जो है 4 मीटर, और इसमें हमें क्या दिया है? आधार की भुजा, इसे हम मान लेते हैं a, ये क्या है? 1 मीटर। तो हमारा सूत्र हमें क्या बताता है कि आयतन क्या होता है? आयतन होता है वर्गमूल 3/12 a की घात 2 गुणा h। तो ये किसके बराबर होगा? यह होगा वर्गमूल 3 बटा 12 गुणा 1 गुणा 1 गुणा h का माप कितना है? 4, और क्योंकि ये आयतन है तो ये किस में होगा? घन मीटर में। और इसको हल करने पर इसका मान आता है वर्गमूल 3 बटा 3 घन मीटर। और अगर इसको हम वर्गमूल 3 का मान रख दें 1.732, तो इसको हल करने पर हम पाएंगे 0.577 घन मीटर। तो ये तो हमने आयतन ज्ञात किया। अब आइए कुछ इससे थोड़ी सी विभिन्न परिस्थिति का हम एक प्रश्न और लेते हैं और उसे हल करते हैं। एक लंब पिरामिड का आधार समबाहु त्रिभुज है, उसका आयतन 50 वर्गमूल 3 घन मीटर है और उसकी ऊंचाई 6 मीटर है। आधार की भुजा ज्ञात कीजिए। अब इस प्रश्न में हमें क्या जानकारी दी गई है? हमें बताया गया है पिरामिड का आयतन कितना? 50 वर्गमूल 3 घन मीटर। और क्या बताया गया है? उसकी ऊंचाई कितनी? 6 मीटर। और ज्ञात क्या करना है? आधार की भुजा। तो इसके लिए हम सूत्र लगाते हैं आयतन का। आयतन क्या होता है? वर्गमूल 3 बटा 12 a की घात 2 h। और किसके बराबर दिया है हमें? यह दिया है 50 वर्गमूल 3 घन मीटर। अब यहाँ पर जो हमें मान पता है उसे हम लिख देंगे। हमें किसका मान पता है? h का मान हमें ज्ञात है, कितना है? 6। तो यह हो जाएगा वर्गमूल 3 बटा 12 a की घात 2 h की जगह क्या लिखेंगे? 6 बराबर है 50 वर्गमूल 3 घन मीटर। और यहाँ से हम प्राप्त करते हैं a की घात 2 बराबर है 100 के, और जब हम उसका वर्गमूल लेंगे तो हमारे पास आएगा a बराबर है 10 मीटर। तो हमें आयतन दिया था और हमने क्या ज्ञात किया? हमने ज्ञात किया आधार की भुजा को। तो इस प्रकार के प्रश्न अब आप स्वयं भी हल कर सकते हैं। अभी तक हमने क्या सीखा? पार्श्व पृष्ठ क्षेत्रफल ज्ञात करना। पार्श्व पृष्ठ क्षेत्रफल क्या होता है? 3/2 गुणा a गुणा l, जहाँ पर a क्या है? समबाहु आधार वाले त्रिभुज की भुजा और l क्या है? उसकी तिर्यक ऊंचाई। यानी कि हम कह सकते हैं कि पार्श्व पृष्ठ क्षेत्रफल होता है 1/2 गुणा आधार का परिमाप गुणा तिर्यक ऊंचाई। और संपूर्ण पृष्ठ क्षेत्रफल क्या होगा कि उसमें आधार का क्षेत्रफल हम और जोड़ दें तो वह होगा पार्श्व पृष्ठ क्षेत्रफल जमा आधार का क्षेत्रफल, यानी कि 3/2 AL जमा वर्गमूल 3/4 a की घात 2। तो आप इस प्रकार के और प्रश्न ले सकते हैं, उन्हें स्वयं हल करिए। अगर कठिनाई हो तो आप उसके लिए अपने अध्यापक से संपर्क करें, और अगर आप चाहें तो हमें भी संपर्क कर सकते हैं।
Highly technical civilization. Electricity is generated at power stations. It supplies the energy required for lighting and operation of equipment in factories and industries. Industrial production depends on electricity. Modern electronic devices for information, broadcasting and communication also operate on electricity. Electric power drives locomotives for better and efficient operation. Lifts in offices operate on electric power. Medical electronics, which can now diagnose illnesses, operate on power. Electronics for entertainment and domestic work also require electric power. The operation of air conditioners also depends on electrical power. In large offices, various types of office automation equipment and computers cannot operate unless electrical supply is available. In our homes, the electric supply helps provide the light. It is required to operate various other home appliances as well. Here you see a thermal power station. It generates electricity for our consumption. The electric lines from the power station deliver power through high-tension cables to substations. The electrical power is converted to suit the requirements of our homes. The power is then supplied to our home for domestic use. Two wires are taken out from the mains and connected to the mains board in the home. This consists of the fuse, the meter, the main switch and distribution boxes. Connections to operate the different types of equipment in the home are supplied via these fuses. Fuses of different ratings are fixed on the distribution board for power equipment current ratings of 5 amperes and 15 amperes. The electric supply is 240 volts AC, 50 Hz in our homes. The two wires, called live and neutral, supply the power. Television sets, light bulbs, fans, tube lights and other electrical appliances require 5 ampere current. Switches and fuses are always connected to the line wire. Fuses are used to protect the electrical circuit in case of overload, that is, if the current in the circuit exceeds the unit. If they are in the neutral, lamp and power sockets would be live when switches are off. An electric shock will be felt by touching the electric line when it is switched on. Fused plugs are used in the house wiring circuit for safe operation. The earth pin on a 3-pin plug is connected to the metal case of the appliance, which is joined to the earth by a path of almost zero resistance. These are wired as shown here and have their own cartridge fuses. Every device and appliance is connected in parallel, that is across the live and neutral. They receive the mains 240 volts AC. The live and neutral wires run in 2 complete strings round the house. Switches are fixed on a suitable board through which equipment like lamps, fans and television sets are connected. If the live wire touches the case, a large current passes to the earth and the fuse blows. Thus, it protects the wire from the fire. Loose wires may cause sparking and lead to fire. Defective insulation and loose, bare wire should not be left as such in any part of the electrical wiring system. Electrical switchboards are not often maintained properly. Too many loose wires and connections are made. The careless habit of not earthing plugs and fuses is often responsible for fires. Here you see an electric iron. You can observe how the cable is connected. A rubber grommet is placed at the point where the cable enters into the appliance. It protects the cable and prevents from being worn out. The 3 wires, namely live, neutral and earth, are connected to the socket inside. The earth pin is connected to the metal case of the appliance. The live and neutral wires are firmly connected to the pins of the socket. If the live wire touches the metal case, then a person may get a shock. But if the earth is connected, then a large current passes to the earth and blows the fuse in the circuit. Thus, the earth wire protects the person from shock in case the person touches the metal body of the equipment. Similarly, the shoe at the other end of the press should be connected with live, neutral and earth. The live wire is usually red, the neutral black and the earth is green. These wires should be fixed and tightened properly. If they are connected loosely, they may touch each other and cause a short circuit. After properly securing the wires in their places, the cover should again be tightened with screws. The plug can then be inserted into the main supply for operating the press. An immersion heater, which is used to heat water, may give a shock if the live wire touches the outer body of the heater. As water conducts electric current easily, one can get a severe shock if the water is touched accidentally. The earth wire should be connected properly and it should be checked thoroughly so that the earth is available. A room heater, which is used to heat rooms in a house during winter, operates on electric power. The heater is connected with a 3-pin plug. The body of the heater is made of metal. Therefore, it is essential that it has a proper earth connection. Loose, bare wires should not be left as such in any part of an electrical wiring circuit. In case there is a short circuit, that is, if the live and neutral wires touch one another, a large current passes to the earth and blows the fuse in the circuit. All the wires should be connected neatly and properly. The proper size of fuse wire should be used. There are various ratings of fuse wire. For example, for lighting circuits, fuse wires which can pass currents up to a limit of 5 amperes should be used. If thick wires are used, then the fuse will not blow and it may damage the equipment and burn the wires.
MCB, miniature circuit breakers, is a modern alternative to a fuse.
They have the advantage of being instantly resettable by a switch or button and of breaking an overloaded circuit in less than 1/100th of a second. Proper insulated tools should be used while working with electrical equipment. If you are working with a 240 volts main supply, you should use insulated tools, otherwise you may get a severe shock. Whenever a connection is made by using 2 wires, the joint should be insulated by insulating the wires. If a person is standing on a wooden plank, he may experience a shock, but the current passing through the body and the wooden plank will be less. To be careful, a person working on electrical equipment should use rubber gloves and insulated tools. All the electrical equipment that we use in our homes or in a factory should be wired safely. Sparks at switches and heating appliances are the main causes of fires. Electric fires are best fought with a carbon dioxide or powder extinguisher. An electric current passing through the body causes electric shock. Harmful effects can be produced, especially on the heart, the muscles and the nervous system. The severity of the shock depends on the value of the current and the time for which it passes through the body. The value of the current passing through the body depends on the voltage applied to the body. If a voltage of 220 volts is touched by a man standing in direct contact with the earth, it will give a very high shock, which may cause death. If the man is standing on a wooden plank, he may experience a shock, but the current passing through the body and the wooden plank will be less. Even in this case, the current passing through the body could give a severe shock. If the shocked person is still touching live equipment, switch off the supply at once. If it is not possible to switch the supply off, pull the victim away using a dry, non-conducting cloth or a rubber mat or a wooden plank. Do not use your bare hands. Lay the person on a bed carefully and send for a qualified doctor. If the heart has stopped, try to restart it by striking the chest 3 times over the heart. If breathing has stopped, lay the patient on his back and clear any obstruction. Take a deep breath, opening the mouth wide, and blow into his lungs. Watch his chest rise and fall. If the patient is shocked but still breathing, keep him warm. Do not give any drinks. Touching a hot iron or heater may give shock or burns. Cool the affected part with water. When you are working with any type of electrical apparatus, observe safety precautions. The electrical equipment and tools should be handled carefully while working in a laboratory to prevent shock. Observation of safety precautions will help to prevent accidents. Mains plugs must be correctly connected to the outer cover of the cable secured by the cord grip and the correct fuse fixed. Cables to equipment should have a rubber grommet where they enter the metal case to prevent insulation wearing. Earthing regulations should be fulfilled by each consumer. The body of any electrical appliance should be connected to the earth pin in the socket. When you are working with any type of electrical apparatus, you should observe safety rules. Proper insulated tools should be used. Students who perform experiments in laboratories in their schools should try to understand the working of the instruments which they have to use. A multimeter, which can read voltage, current and resistance, is a useful instrument. Electrical and electronic equipment which works on 240 volts main supply should be handled carefully. The earthing of the equipment should be checked with a multimeter. If you have to replace a fuse, check the fuse for continuity and use a fuse of the proper rating. Also, check that the live point does not touch the body of the equipment. Proper tools, which are covered by rubber lining, should be used. Care should be taken when using the tools so that the uninsulated portion of the tool is not touched by hand. Do not use the same plug point to operate more than one equipment. Use an extension board to connect 2 or more devices for power. Soldering irons work on 240 volts AC lines. Therefore, you should be careful while soldering joints. You may get a shock or be burnt if you touch the hot end of the iron. Do not insert loose wires to operate a piece of electrical equipment. Always use a proper shoe. Check the connections before you use such a device. In factories, very often fire and other mishaps occur due to poor maintenance of electrical equipment and lack of proper upkeep of switchboards and electrical wiring. This may cause short circuits, which can endanger the life and health of workers. Protection from electric shocks can be ensured by observing safety measures and following correctly the regulations for the electric supply system in the factory.
गर्मियों की छुट्टियों में बच्चों की रचनात्मक क्षमताओं को उभारने के लिए CIET द्वारा विभिन्न कार्यशालाएं आयोजित की गईं। उनमें से एक कार्यशाला में बच्चों ने कठपुतलियों का निर्माण स्वयं किया, जहां एक और उन्होंने विविध सामग्री से अलग अलग तरह की कठपुतलियों का निर्माण करना सीखा, वहीं उन्होंने छोटे छोटे नाटकों की रचना करके उन्हें मंच पर प्रस्तुत भी किया। तो आइए देखते हैं उसकी एक झलक।
अरे नमस्ते बच्चों, मैं फिर आ गई, तुम्हारी दादी, और आज मैं तुम्हें एक कहानी सुनाऊंगी, तो जरा गौर से देखना, खूब मजा आएगा। आई लव माई इंडिया, आई एम एन इंडियन, आई एम प्राउड टू बी एन इंडियन।
आप इस उम्र में इंग्लिश पढ़ रही हो?
बेटा, पढ़ाई लिखाई की कोई उम्र थोड़ी ही होती है, पढ़ाई तो किसी भी उम्र में की जा सकती है। खैर, तो बताओ तुम यहाँ कैसे?
दादी मुझे नींद नहीं आ रही थी, तो कोई कहानी सुनाओ ना।
अच्छा, सुना देती हूँ। और जो कहानी मैं तुम्हें सुनाने जा रही हूँ उसका नाम है खरगोश को मिली सीख। बच्चों, तुम भी सुनना, खूब मजा आएगा। तो सुनो, एक बार 2 चिड़िया थीं, गुनगुन और मुनमुन। दोनों जंगल में उड़ती जा रही थीं। अचानक कालू कौआ उन्हें खाने के लिए उनके पीछे पड़ गया। दोनों चिड़िया खुद को बचाने के लिए खरगोश के बिल में घुस गईं। कौआ उन्हें ढूंढता रहा और जब उसे वे नहीं मिली तो वो भी उड़ गया। तभी खरगोश वहां पहुंचा।
मेरा तन डोले, मेरा मन डोले। अरे, तुम दोनों चिड़िया मेरे घर में कैसे घुस गई? निकलो मेरे घर से, निकलो। खरगोश भाई, हमारे पीछे कौआ पड़ गया है, वो हमें खाने वाला है, इसलिए हम
लेके जाने के बाद
अब तो कौवा चला गया ना, निकलो मेरे घर से। धन्यवाद खरगोश भाई, हाँ आपने हमारी बहुत मदद की, हम भी आपके किसी काम आएंगे। तुम तुम दोनों छोटी छोटी चिड़िया मेरे किस काम आओगी?
घमंडी खरगोश हंसता हुआ बोला कि तुम दोनों छोटी छोटी चिड़िया भला मेरे किस काम आओगी। लेकिन उसे तो पता ही नहीं था, एक बार वो भी फंसा।
हाय राम, बचाओ बचाओ, खुजली हो गई खुजली। हे राम, खुजली हो गई खुजली, खुजली बचाओ बचाओ। हाय राम, खुजली हो गई। डॉक्टर तोता, मेरी खुजली को भगाने के लिए कुछ करो ना। खरगोश भाई, मेरे पास खुजली भगाने के लिए कोई दवाई नहीं है। हाय राम बचाओ मुझे खुजली।
तभी दोनों चिड़िया उड़ते हुए वहां से जा रही थी। उन्होंने देखा कि उनका दोस्त खरगोश तो मुसीबत में है।
खरगोश भाई, तुम्हें क्या हुआ? मुझे खुजली हो गई रे, बचाओ, खुजली हो गई। अभी हम तुम्हारे बदन से सारे कीटाणु बीन देते हैं।
और इस तरह दोनों चिड़ियों ने खरगोश के शरीर से सारे खुजली वाले कीटाणु बीन दिए और उसकी खुजली ठीक कर दी।
धन्यवाद चिड़ियों, और मुझे माफ करना, मैं उस दिन बहुत घमंडी हो गया था और सोच रहा था कि तुम छोटी छोटी चिड़िया मेरे किस काम आओगी, लेकिन अब मुझे सीख मिल गई है।
और ऐसे उस घमंडी खरगोश को सीख मिल गई कि हर इंसान की अपनी एक शक्ति होती है। हर इंसान किसी ना किसी तरह किसी के काम आ सकता है। ना कोई कमजोर है, ना कोई बलवान, ना कोई छोटा है, ना कोई बड़ा, सब बराबर हैं और हम सबको एक दूसरे की मदद करनी चाहिए। तो बच्चों, मजा आया? मुनमुन, मजा आया तुम्हें?
हाँ, बहुत मजा आया दादी।
तो चलो फिर अब हम चलते हैं। बाय बच्चों।
बाय।
मित्रों, आपको हमारे कार्यक्रम कैसे लगे? आप अपनी प्रतिक्रियाएं और सुझाव हमें भेज सकते हैं। हमारा पता है किशोर मंच, CIET NCERT, श्री अरविंदो मार्ग, नई दिल्ली 110016। आप हमें ईमेल भी कर सकते हैं। हमारा ईमेल पता है ciet.kishormanch@gmail.com और हमारे टोल फ्री नंबर हैं 1800-111-265 और 1800-112-199।